Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So thank you for joining me this evening. We've got some fun things to talk about tonight. And most of this is things that came out of the last presentation. And it's necessary to talk about these things because it's necessary to talk about them before we do the second part of something electric. And I think you'll understand why by the time we get to the end of it. Also, it helps me deal with something that I've wanted to deal with, or rather a lot of other people have asked me to deal with for some time. So I can kind of get that out of the way and I can move on with what I'm interested in, which is fixing Fukushima and the energy situation. So can you hear me, everyone? Is that, I just want to check if people can hear me, so let me know. Okay, sound is good. Excellent. Okay, so let's just crack right on with it. So I shared this slide earlier today, and this is a composite that I made up. And basically, I have talked about this one in the Sochi presentation, and I will show you those slides again, or that slide again. But this, as I understand it from speaking to John today, this sample was produced probably in about 1988 in Canada. And this actually is a very large aluminium sample. I mean, it's physically large. And the structure that we're talking about on here, this one that I'm showing you here on the right, this is basically an affected area in the center of this material that came out to one side. Whether he cut it in half again, I don't know, but it's completely affected. And I can show you the inside of that because we have the cut here. But it looks like it has this kind of slightly skewed hexagon going on, and this little tail out the end there. And we showed that I believe that was some sort of Euler-type spiral coming in here, in terms of the flow of the material. And you can see that in the 3D sense when you look at the cut division. Now, I think basically the material emptied out from here, and John just kind of like filled in whatever before he cut it, so that if there was any thing that could be able to be broken or whatever, I don't know, or it might be that this lump of wood went in there. I don't know, but when I originally looked at this, I thought it was very, very surprising, but also my skeptic's head on, I'm thinking, you know, is this real, or is this something that can be machined and stuff? So I wanted to study it for a period of time. Actually, the samples I think in New Mexico, but anyway, I haven't actually held this sample in my hand, and I do hope to hold it in my hand later this year, so I can have a much more in-depth study of it. But I had this question, I think I discussed it, about this little nick up here. I couldn't understand what that was because it wasn't quite this kind of triangle that I was seeing in other aspects of the technology. And it wasn't until I clocked that it was actually part of this overall structure and the sweeping in and this spiral that it made sense in its own right. But there's a sequence of events happened this week, and I went to go back and look at a video I took of the Bullburn sample on, I think it was the 7th of, or rather I published it on the 7th of March 2018, I believe. And I was just going through that, and I came up and saw this structure. And I was absolutely astounded. I said to myself, that's the same structure as on the aluminium. So this is from 1988, and this is from 1986. Now, the difference between these two structures is this one is extremely large. It's extremely large. And this one, as you will find out as we go through this presentation, is at the broadest part around about 400 microns. 400 microns. And it has sort of round sections in them. In fact, if I go to the next slide, you can see it without all the gummins on there. So, it has these kind of like scalloped areas around here, these curved kind of scalloped areas, but it has this overall hexagon shape, which if I play the GIF animation here, This is exactly the same shape, exactly the same shape. It's not distorted in any way, but it is a near one-for-one match. And what's even more striking, if I actually can move my mouse off here. Oh, no, that's the next slide. I always wondered what this was, and I just thought this was kind of like damage. It was damage to the... well, it is damage to the aluminium, but I thought maybe this is kind of damage when he was doing the machining or whatever. But the amazing thing is, there's this same damage down here. This same shape here. Except this is 400 microns across. Can't remember what the scale is and must get the scale, but it's very large. It's very large. So the idea that this structure was machined in some way is completely out of the window for me now. Completely out of the window. I have no doubt in my mind that this is the same effect going on. And since the ball burn sample has every single signature I can possibly imagine you would see in a multiple coherent matter ball lightning type affected material, this must be also ball lightning. And it also, I'm happy to see that this is much more well defined. The curvature up here is a bit choppy. It's a bit choppy here and a bit choppy here. And I've talked about this in the past. Firstly, it's a little bit choppy here because the actual lines that on the top of the steel from its original machining, the structure has gone through there, so it's actually having to remove more material at this point than it is here, where this is kind of like a cut. It's either a cut through the whole structure and it happened inside the structure, or it came out of the surface or went into the surface. But it's a much harder line. It's a much harder line, and you can see this in other samples that John has where aluminium has been involved. Where, for instance, a piece of wood has gone right into the center of a piece of aluminium. And the wood, even on 400 times or whatever magnification, there is no burning of the wood piece that's gone inside of the aluminium. Which, as we know, Fahrenheit 451, that's the temperature at which paper burns. So you can't have a scenario where even aluminium can be mixed with wood without the wood being charred in some way. So I've said since early 2017 that whatever it is, it affects different metals differently. And in the case of aluminium, the strength of the lattice bonds, kind of determine the melting point. Okay, and in aluminium, it's 700 and whatever degrees, around there. And in iron steels, you can get some steels that are melting at, 1,300 something centigrade. But higher and lower, but around that. But it's much higher. And also the conductivity, I've said, plays a role. And aluminium is much more conductive than stainless steel. It's much more conductive thermally than stainless steel. Stainless steel is actually a really bad conductor thermally, but as I've said before, I do not believe that this is a thermal process. Yes, you can get things that look glowy. They can be yellow to orange, but this is, in my view, exotic vacuum objects, EVOs, itonic clusters, whatever you call them, ectons. They're coming to the surface and they're disheveling. And they are firing. Firstly, if they're growing, they're emitting UV and 2 kiloelectron volt photons in the soft X-ray. But if they're disheveling, they will emit higher energy. Shishkin says around about 10 keV. And you can get, if a big one blows up, you can get very high energy, all the way up into the sort of gamma energies. But typically, they're not doing that. But even if they're at the 2 keV or 10 keV range, that is going to ionize the air around the surface of the metal. So you're going to get metal that looks like it's hot, but it's not hot. It looks like it's hot, but it's not hot. It's just an ionization effect, local. And it probably would have no to nil temperature when you touched it. That's not to say that in the case of aluminium, it wouldn't actually be soft to the touch until the EVOs have kind of got beyond a certain level of coherence. Okay? So what I've said for a very long time is that aluminium will be very highly affected. I didn't need to be a genius. John's videos showed that in the 80s. So this is obvious. And what is also obvious, steel is okay, it's okay, it's okay, and then it snaps. And I've described that on the monopole video with the spanners that the CIA looked at, where you have two norths together and two souths together. And this is because I believe you get the monopole, pseudo-monopoles, building up to such a strength that their field strengths interact, and at some point, they're not melting the metal. They're not melting the metal. They are not melting the metal. They might be eating the metal completely, but they're not melting it. But when you get the fields interacting, they literally rip the metal apart. It literally brittle fractures, and it slides to the side. But the field is non-linear. It's extremely intense, the field. Okay, so that putting aside, if you look at it here, you've kind of got these round bits going around. And when we start to get to the end of the presentation, to something that was shared and published yesterday, as a first in science. Oh my God, John did it all. He did it all. But anyway, a first in science. Okay. You're going to see something very similar to this. Very, very similar to this. Okay, so I've got the videos up here to the previous videos that I've shared where you can see this, and you can download the high-res images of this sample, and there are other images of this, and we can even look at this live on the microscope. I think I've actually got this particular structure on the microscope. So let me have a quick look to see if I can pull that up. So I think, is that the right one? I don't know. Is it that one? I don't know. Oh, here we go. I think this is it here. It might be, or it's a similar one. It's a similar one. It might be the same one. I think it might be the same one. Do you think that's the same one? I don't know. I'm looking at it for the first time on the microscope since I published that video on the 7th of March 2018. So is that the same one? I think it might be. Anyway, it's a very similar one. So let's have a look in that at a higher magnification. If we can not lose it, that would be good. Okay. So maybe that's the same one, I don't know. Anyway, I haven't had a perfect look at this under SEM because I didn't really realise the importance of the structure back then, to be fair. So that's that on the microscope. So there we go, and there we go. So what I've done to take the picture that you're looking at there, I've used this Narugo on a Samsung S7, and the reason I use it at Samsung S7 is because it has just a 12 megapixel image sensor. It just has one. There's no artificial intelligence trying to make a picture beautiful with perfect skin tones and fake hair. You know, it's actually real. It's not trying to fake anything, and it has a very large pixel size, so it's very good with this. So yeah, so there we go. Are we seeing the same thing? I think we probably are, and it's just on a very different scale. Okay, so let's go and look at the first of the two here. So this is the structure we've just been looking at, and you're not looking at that. I'm trying to show you this slide. So this is the structure we've just been looking at on the previous slide here, this is cut open, and this little nick here is what confused me for so long. This little nick here, because it's this bit here. This little nick is this bit here. I confused this for potentially one of these triangles, which is the right shape for the triangle, but where I've got it blown up over here. So I was just confused with this one for so long, and anyway, I talked through that before. So you can see that this is in here, and I would imagine that the structure is on the top here, spiraling around with this tail, and that would be the same for this. It's on the top, spiraling around. You can see the ring, and you can see almost the vortical nature to the way it's destroying. This is more like the heavy event horizon. So this is not a sphere ball lightning, according to Matsumoto. There's two versions. You get of typical. You get the sphere and you get the toroid. This is more a toroid one, but it's a toroid which has got these kind of divisions going on. I imagine you can work out how many are there. And you have a diameter, and this is the event horizon on this one. Okay, so the special on the topology for a sphere and a toroid. Okay, so so inside here, you can imagine that if the thing's spinning around on the top here, and this tail here is up here, that maybe it's wobbling a bit in there as it grows. So it grew out here, or it grew out here, and then it just flipped over to here. And this triangle here is a much larger version of this, in my opinion. This triangle here is a much larger version. This is another much larger version, but anyway. And there might have been other ones in there. So if it did grow from the center and grow out, then maybe there was one that came out, or maybe it turned into the bigger one. I don't know, but it is the same thing as from the top view. Okay, so I've actually got an SEM here of the ball burn sample. And I took this in the Masaryk University, I think in beginning of 2018. Anyway, so we're going to come and revisit this structure over here in a minute. But this is what I've just been showing you on the microscope here. This structure here is what I've been showing you on the microscope. So, okay. And it's this structure. And if you notice that, at least on this image, you can see what I was showing you on the previous one. It's got a central area that's different from the outside. And this is from the 2018 submitted paper. It's final form, October the 23rd, 2018. So this was published. This video of this was published on the March the 7th. This is October the 23rd, 2018. This is from plasma flow discharge. And so what the Bogdanovich et al. Team were doing at the Moscow Physics, Nuclear Physics Laboratory is they had a water flow, and they were discharging high current short pulses through the water into a metal plate. And what they observed was 2 days after the experiment was run, they would see these things moving around on the metal plate, glowing on a metal plate, at a luminous toroidal object that performs translational and rotational motion over the surface of the electrode 2 days after the plasma flow discharge. So I've got the paper there, and I've shared it before, and we can look at that if people are keen at the end. But I believe that that is the same kind of structure that you are seeing here, and I believe that if you looked at the inner part of this rather than the glow, which is very smoothed out, I think you would see a hexagonal structure, and then on the inner side of that you might see an actual hole, but the whole thing is just overall glowed out. So there we go. So that is that, and I have a different type of SEM here, which the first one with the black bits is looking at the actual elements on there. The second one is giving you more depth perception. Okay, so there's not a lot of depth in here, but there is depth in this center bit. So you can see this is curved hemispherical in here, and this is the structure that we're looking at before. So you can forgive me, I think, because I didn't realize it was so significant. I was more interested in this, and you can see the trefoil down here, and you notice 2 of them are very big, 2 of them are deep, the other one is not so deep. 2 of them are very big and deep, the other one is not so deep. We're going to revisit that probably on Sunday, if all goes well. And here you can see the really big yin and yang with exactly the same shape. It's basically a hexagon, but these 2 points have been drawn out into a point here. And one is the hole and one is an affected surface. Okay, so there we have it. Now, I said I would come to this structure over here, and this was one of the first images that I took with that structure here. And it's not actually this light, it's actually what's called a cyber light, and it hasn't got such a diffuse area on here. It's actually a compact fluorescent that I was lighting this with. and it produces a harder, crisper edge than this particular studio light. And I used a Canon 7D that I purchased in 2012, and this macro light that the community helped me buy. Thank you very much for those people that made that possible. Okay, and that's just macro photo here. So this was the first real shot that I took of this. And as you can see, you've got the affected area, and then you've got this kind of slight fall off, which we've looked at in detail. And then it looks like there's a sphere in there. And I went to and fro as to whether there's a sphere in there. And you'll see why in a minute. So I could, this is about as close as I could get with this macro, with this 18 megapixel camera with the Bayer pattern on it. So that was about as close as I could get. But I was convinced that what you're seeing there is the reflection of a sphere, a glassy sphere. And on the other side, this light here was the internal reflection from the back side. And I know a lot about this because I studied retroreflective materials, because I was going to run a business creating retroreflective materials for green, blue, red screening, where you just put a ring light on the camera years and years and years ago. So this kind of made sense to me, but I needed to get a closer look. And that's when I went and bought the Narugo. But what did the Narugo give me? Well, here we go. We got the Narugo, and it has a light guide where it takes the light for the Samsung S7 and it feeds it down to a ring light. So it converts the light from your LED in your phone into a ring light. And it also polarizes it on the way. So this is quite good. This is your focus ring on here, which you do prior. So this is a little device, and it's just $70. And this is the kind of output it gave me. So here we've got a spiral. This is a Paisley structure going into the spot there. So this is another classic kind of a ball lightning type damage, and we saw something similar in the last presentation on the wall of that Hungarian home shared by Dr. George Eagley. This one it's a spiral on this side and then a different spiral on this side. You can see a spiral on this side, and you can see the vortical structures going in here, and you've got vortical structures. So this for me is more similar to the kind of marks that we're seeing in the ultrasonic kind of pieces of aluminium that get ripped out from the ultrasonic tank. Anyway, so what did it look like when I looked at it with this? Well, okay, this is not ideal. What we can see is a little bit more detail. You can see the lines here, and I can't see the fall off here, and I can't see whether this is a sphere. Now, it does look like it has a kind of line here and a line here and a line here, and I don't know, it's not, I wouldn't call it necessarily a hexagon, maybe more sides to it. But it does look like there is a definite change in refractive index. Suddenly, there is a line of something that is wetted to the metal surface here that then is changing the refractive index of the ring light. The ring light here, this ring light here, is changing the refractive index. The refractive index on here is changing it so that it is causing this effect here. So that wasn't good enough for me. I knew from this one that really did look like there was a sphere stuck in there. And this is the actual structure to me that told me that this Bullburn sample was so special. There's a sphere stuck in a pit. The sphere, the pit didn't form because the sphere was already there. No, this is all part of the same happening. It's all part of the same happening. So just so you can see it, this is a $70 microscope, and that's that one. So I have this microscope image here, and you can see that this structure is more than 1 millimeter across here. And if I click here, you can see a little bit different. So on the scanning electron microscope, you kind of have, for one of it, you still have this wetted effect. You can see the hard line here, with a little bit of waviness, like we saw in that other structure. But in this one, you can extremely easily see that the there are cut lines. There is a scalloped area here. It's not just that you have a curved here. You have a scallop that goes all the way down, okay? A scallop here that goes down, a scallop that goes down, okay? And it looks like it goes towards a polar area down here. Does it? I don't know. We've got a scallop here, a scallop, okay? So these are little bits that are taken out. And this is the kind of thing that you get when you have a vortex. You get these kind of little bits that are around the vortex, which are also round. And you're seeing a part of the effect of that. Maybe. But what is very clear is that that is a hemisphere underneath. And this is why you need to use different technologies when you are trying to characterize materials. But here, on the right, I was able to capture, with a lot of hard work, another shot where we have a very clear image of the square studio light captured in the glass. So this, for me, said yes. What we are seeing in this image here is a sphere. It is a sphere. It looks like there's some internal reflection on the other side. What I don't know is these two, it looks like you've got two reflections. Now, is that an artifact of a blur? Maybe. I think it probably is. I think this probably is a solid ball. What gives me pause for concern is that Anatoly Klimov and other authors, for instance, Slobodan Stankovic. So Anatoly Klimov, in his Tesla-inspired spiral flow, spent quite a lot of time working with shoulders system. He gets little spheres, and they are often hollow. They're just like a micron or two thick. And in the case of Slobodan Stankovic, he used a hydrogen HHO torch on carbon, and he got some hollow type spheres, or certainly lead spheres. So I'm not so sure this is definitely not a hollow sphere. But if it was a hollow sphere, it would make sense, because if we're saying that the material is coming from the environment and it's condensing into this coherent matter layer, okay? And what we get out of these systems is a lot of diamond, okay? We get a lot of diamond. Then could it be that that is a diamond sphere? Could it be a hollow diamond sphere? And that it is that coherent matter layer that ends up becoming that, it's like a spherical diamond structure. It's like a perfect buckyball, just like you see under the food dragon, or the food dog, in front of the central temple in the Forbidden City in Beijing. Okay, so I wanted to show you that, and the reason also that I feel that it might be a sphere is because of the work of Bychkov. Bychkov is a Russian who has done some amazing work on the study of ball lightning, both attempts to artificially produce it and actual real ball lightning. And there was a presentation that he did last year, and it's shared on the Martin Fleischmann Memorial Project's YouTube channel. I recommend you go and see that. But this is what I would call the money shot from that particular presentation, and we will go there now, and it's this. This is a hole in the glass made by ball lightning. To the right, there is a hole in the glass. To the left, there is a disc that had fallen out of the hole. The disc hole axis sizes are 8.2 and 7.6 respectively. So I guess this is the axis, and maybe he's saying that there is a difference in scale between this and this, i.e. the distance between this node and this node, and this node and this node, is this one is slightly different. It would not surprise me. I would suggest that this was cleanly taken out by the coherent matter layer on the exotic vacuum object. I would suggest that it came into the glass, and at the point of being 50% in the glass, It got stuck there. It got stuck there and got excited. Sometimes ball lightning can go straight through the glass because it is neutral. It can carry anything inside it in a neutral way, which is bizarre. But anyway, it's coming in here and it gets stuck. And one of the reasons I think it might definitely be getting stuck is that you have these two poles. You have, in my view, this is the North Pole where it would be doing something and throwing something out, and down the bottom it's pulling it in. Or you could think it was the other way around, but I think it's pulling it in here because we see where this little notch on this side and we see an affected area up here. So I believe that what you are seeing here is absolutely, as they say, the effect of ball lightning. And if this is this case, then this is the circular field that surrounds the structures inside. Okay, and it's the coherent matter layer here that did the work, and these are the poles. Remember, we saw poles very clearly on the iron oxide, the magnetite or mahemite or whatever it is. I can't remember the other one. Magnetite rich iron sphere with a crenellated surface from Me 356. You could see the pinching to the poles, and there was a little bit of that going on with the magnetite mahemite sphere that or spheres that were produced with the ultra process. And it would be good to do a lot more studies to see if that really is the case, that there is this pinching going on, and then we would know that there is a good north and a good south pole, or maybe a suppressed north and a strong south, or whatever. But anyway, the spheres could actually be a cluster of them all coming together. So I then was lucky enough to with the help of the crowd and front running it, but anyway, to get the Dino Light Edge, and that gave me a different look at it. And so this is what we saw with the Dino Light Edge. And so at this point, it becomes very clear that we have something in this pit. We have something in this pit. Now, if you remember, this is the flat metal surface. This is the affected metal surface with the transmuted areas. And you get like spheres, subspheres within this structure, which are nearly pure iron. And then you get a lot of carbon deposited in these holes, which is what we would expect with exotic vacuum objects. Then you get this area around here, which I would suggest is the double layer, where this is the center of the double layer, and I would suggest that the boundary layer here, the event horizon, this is coherent matter at this point. This is normal matter that's being just left alone. This is matter that is affected in the effect field, and also there might be self-similar quanta flying around this, you know, coming out and flying around, orbiting or whatever. Okay, and then as we get in here, we start to get to what I would think is the double layer area, and you get a very large change in the field here. And at this point, I would imagine that this is probably something like electron degeneracy pressure, where they literally cannot get any tighter, that you've got it as coherent as it possibly can. And it's actually the fact that you have the pressure pushing it out, and its desire to pull the electrons in with the ions and whatever else, that forces the entire thing to become coherent. Because if you have like one, it's kind of like a very stiff but slightly elastic membrane. Okay, it's pushing out and everything's coming in. They're all coming in at whatever temperature they are, but when they get to that, it's like they all come down. They have to give out energy. This is the condensation process. Remember, plasma to steam, give out energy, condensation. Steam to water, give out energy, condensation. Water to ice, give out energy, condensation. Ice to coherent matter, it has to give out more energy, doesn't it? You know this from making Bose-Einstein condensates by taking it to absolute zero. You have to get rid of the energy to take it down to absolute zero. Except in this case, you don't have to. You just have to get it to all the same energy. It might be very cold. That's a good thing. Think about that. So anyway, the point is that at this point here, this is the point of no return. Now, it might be that it grew. It might be that it grew. So it was very small. It was very small. And as it grew, it consumed more matter. You had more coming in, and that meant that the boundary had to grow to accommodate the more things coming in, and then it had to grow more. And as it did, it removed a spherical structure from here. But because it's magnetic, and I would imagine the pole is up here, like this is the pseudo pole up here, and this is the pole down here. So this is stronger than this one. This is like the Boyd-Bushman patent, where you have a whole bunch of magnetic stuff up here, and it's all pointing into a central point, and then you don't have something down here, so you end up with a pole. And it could be a north one, or it could be a south one. But anyway, that's the point. So you have a magnetic point in the center here of everything that's going on here. And it just basically rips matter apart. It just rips matter apart. So I have here, looking at the bottom of the hemispherical structure, and in this second section here, no, sorry, if I can pause it, can you let me pause? You can pause it. Okay, here you can see what I've done in here is I've focused right on the bottom using the Dino Light Edge 3 Plus. Okay, and as we come out, we see it starts to get unfocused, unfocused, unfocused. This means this is hemispherical. So this exactly supports the observation that you see here in this one, where if I go and stop it there, this is hemispherical. This is absolutely, without a doubt, a spherical structure that's in here, and I believe that is confirmed by this lighting over here. And this is confirmed by the structure that you see here. So this is the fall off on the focus here. And you have this change in refractive index. The only question I have that remains is this a thin structure or not? Now, what is it? What is it? Well, we looked at this the other day. And if you look at spectrum 61, when I did spectrum 59, there was not many counts. Okay, that's because the electron beam cannot get into the bottom of that hole. It can't get into the bottom of that hole. So it doesn't know what it is, so it doesn't give it with any certainty because there's not enough counts per EV. Okay, but in the spectrum 61, so I took an area instead in spectrum 61, and you can see it over here. It's much better. It's not perfect. You want like 20 counts per EV up here, but this is okay. And it's determining that it's 60% carbon in this area and oxygen. Now the oxygen may be on the surface. So if this is 60% carbon here, now bearing in mind that it can see there is oxygen going to be on that surface. Are we looking at diamond? Is that a spherical diamond? Have we synthesized a spherical diamond? Now, Matsumoto says that mostly carbon comes out. Yul Brown says mostly carbon comes out. That is what we have observed. Mostly carbon comes out. Carbon, well, it's the strongest, it's the most covalent, most high D by temperature, strong, whatever. If you were crushing something, that's what it would end up with, in my opinion. So I believe that what we have in this image here, is effectively a sphere, possibly a diamond sphere. A diamond sphere that doesn't have faces. I mean, it does. It would be like a super big buckyball, but they are extremely small. It's like, try and polish. I'm not showing you anything, am I? Sorry. When did you not see this? Okay, all right. Sorry. When did you not see this? Oh dear. Okay, all right. Sorry about that. When did you get to? When did you get to? Tell me what you last saw. What did you last see? Yeah, I know you can't see it. Sorry. What did you last see? Yikes, 5 minutes ago. Oh no. All right. Okay. All right. Did you see this? last saw glass. Okay, so you last saw the glass. Okay, I'm very sorry. God, I've got to get better at that, haven't I? Okay, so you last saw this. Okay, no diamond. Well, what I'm saying is here is that this side here, this inside here is very spherical. And also it has these scallops that come out. Now you will see these same scallops on the John Hutchison thing, but this comes to a pole. This comes up to a pole, okay? And it almost looks like there's sections to it. You've got a scallop, but there's a scallop within a scallop. So it's almost like it's made of other things. But anyway, the point is that this is a hemisphere that's cut out of the material. Okay, all right. Here, I used a different lighting method. And I was managed to get in there with my macro lens. And I was able to capture this. And I was saying that I had some doubt whether this is a reflection of the square studio light, which has quite a sharp edge to it. And so for me, it was absolutely 100% confirmation that this is a sphere in this slot. And I'm saying that it might have a slight thickness, the sphere, and that's why you're getting this double reflection. It might not be, but I think it might be, because other authors have seen spherical objects. And I'm saying this is the cut ball lightning has gone through this glass. It's, I think, real ball lightning. This is from Bitchkov, and you can go and see this presentation on our YouTube channel. And it has a north and a south pole, as far as I'm concerned, and this is a north and a south pole. I would very, very much like to see the edge of this. I would very much like to see the edge of this. Is the edge of this similar to the fracture sample by John Hutchison? Is it similar to the jewel in Lion? I suspect it might be. So if I am able to go to Russia at some point, I will ask to see this sample from Bitchkov, and I will look with my microscope at this edge. I would expect it to be that same structure. Okay, so then I showed this, which I used the Dynalite Edge 3 plus, and here you've got the non-affected area. This is the affected area where I believe you have smaller quanta of the overall structure. So these are kind of like, they might be monopole pairs, that sounds weird, but anyway, these yin-yang pairs going around here, as we observe in the structure on the outside of Lion 2 quartz. I think it's Lion 2 quartz. But as they come into the center, they get organized further. And they get to this point, which I believe is the start of the real double layer. And as it falls down, it gets to this point, and this is like your springy, strong, impenetrable membrane. And I call it the event horizon, but the event horizon grows. Okay, so it starts off small in the center, and as the ball lightning grows, it grows and grows and grows and grows and grows, and it consumes material on the boundary of the event horizon, which is the coherent matter. Okay, and you can see the clear change in refractive index here. So where this meets this material here, where this meets this material here, and we've already shown that this comes down and it kind of goes down a bit. And we've also already shown that these areas are richer in carbon than the general metal, and that there are spheres in here that have, like this one over here, which is high in iron content. Okay, so I then showed, without you seeing me, oh, go on, he says, this, which is using the Dynalite to focus at the bottom of the pit, and get that in focus, and you can see that the focus falls off as you come up to here. The focus falls off as you come up to here, and this means that it's confirming the fact that that is spherical underneath, and that is why it's extremely important to use a range of technologies to be able to look at your material to be able to properly characterize it. So there we go. That's effectively the top surface, and you can start to see this becomes fuzzy. And there's this boundary where you get this change in refraction. Okay, so then I showed this again. We've shown this before, and so I was talking about spectrum 59 here. It doesn't have enough counts because it's in the shadow of the electron beam from the scanning electron microscope. Okay, so we can't see the bottom. That actually confirms that it's quite a deep pit. okay? Because we can get a good look at stuff around it. So what I chose to do was to get more counts, was to choose a much larger area, and that gave us a reasonable number of counts here. And what it shows is that, at least for what it can see there, now bearing in mind that the beam can go into this and it's quite close to the edge, but even still, it's reporting that 60% of the atoms and only 2.1% of the atoms, 60% is carbon and 2.1% is iron. So basically, between carbon and oxygen, you have 93.4% of all of the atoms in that area. So I would conclude that there's oxygen on the surface. We're picking up some X-rays from other areas. Some, like, it hits this edge here and it bounces. Remember I was saying the other day, the X-ray bounces off the surface, hits over here, and then the photon comes back into the lens. So I am of the firm belief that what we are looking at in this image, and what is causing the reflection here, and what is causing the refractive index to change here, and what is causing this reflection, which I first saw, is a sphere of, possibly a sphere of pure carbon. Okay, and this is what, I mean, when I was looking at this, I hadn't read Matsumoto's work. I hadn't really realized that Yul Brown had observed the same thing. So it was, you know, I was thinking, how can that be pure carbon? It's a sphere. Well, it could be the buckyball. It could be the buckyball. So you can see my thinking at the beginning of late 2017, early 2018, how I was starting to think, well, if this is carbon, then that would explain the carvings on the Temple of Osiris, which are just projections of what this is, and it would also explain what I felt when I was lucky enough to feel when I was 18 in Beijing all those decades ago. Anyway, so moving on, why did I start thinking about this? Well, because of this, and this is from some work at scihub.se. Here, this is you can go and have a look at the paper here. And this was actually published on, I think, the 6th of March, or 5th of March, 2018. And this here is part of a video, and I'll just go and get the video for you, so give me a second. But I'm saying that what they are observing here is essentially the same things that you are seeing here, except these are, what they're showing here in this one here is very, 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 very small. This is large. This is small. This is large. Now, if it may be that there is an event horizon in the center of this, which is very, 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 very small, okay? And they're never able to get it very big. So they don't observe anything like John Hutchison was observing in the 1979 and 1980s, from 1979 onwards. These spherical things taken out of material. I think if they could get this bigger, they would see this. Okay, so let me dig out the paper. Okay, so I'm not going to play all this video through. I'm not going to play it with audio either, but they show these structures forming. This is 0.46 milliseconds, and this is the section that I took the image from, which I'm showing you in this slide here. Okay, so now these form a range of shapes. They do form a range of shapes. That would explain why you see a range of shapes. Okay, but it depends on their orientation, and if they get locked in the metal in a particular orientation for whatever reason, maybe it's a non-magnetic material, so they have more flexibility with how they can get locked until they get to a certain size, and then they're locked in place. Remember what I was saying, the metal on the Hutchison spanners that break in half, or the rat tail file, when the north or south pseudo-magnetic monopole gets stuck in place, it will grow and grow and grow, and so if you can imagine, like for instance, I've talked about this in fact in that same video. So which sample is it? This is not, the fracture sample is not so good for showing this, but I have another sample. Let me get that sample. Yeah, this is a much better sample. This one here. So I described this sample where what's going on is individual parts of this have got a magnetic monopoles in them, or around their crystal grains, their long crystal grains, they've got a coherent sheath which overall has its own pole, and it then splits it, and then they rearrange themselves so that their poles are aligned. And then when the music stops, it ends up like this. So there we go. Anyway. So let me get back to the paper. Not the paper, there you go. So this is this video, and they've got anything else interesting in here. They say about how they form it. And then they say these things. Do these look a bit like the birdies on remoteview.ic or in the Lion core? Maybe. And they've got some different examples here. Now, I've referred to this work at Aalto University in Finland before, because you can see here this is the E field and this is the B field. So you've got the electric field. So this is kind of like your fall off here that we're seeing on our structure. This is maybe the double layer, and this is the magnetic structure that's forming it. Okay, but you know what? It's very, very, very small. It's very, very, very small, and they think they're doing something amazing. No, John was doing this in 1979. Sorry, sorry. They're fiddling around with a few ultra cold atoms and getting really excited about it. So there's your skyrmion. Here's some formations forming, and here this is quite interesting because you can see some of these slightly offset. If I maybe zoom into that, okay, maybe you can see that there. So I'd recommend you go and get this paper. So you've got a slight spiral here with a little lick. Does that remind you of anything? This is an inverse one. Okay, so this is a double spiral. Okay, all right, fine. And then these are some different things, and you can imagine if they were interacting with the material, what they might do. But remember, at the core, there is a very hard core. There we go. So that is why I decided to have a look at that. And so you can imagine actually that this is like the primer fields, and the primer fields is just a logical extension of the Lockheed Martin Boyd-Bushman pattern, which I've discussed in detail. And why do I say that? It's like the Lockheed Martin has a basic 1, 2, 3, 4. There's like 4 around it, and then you can have 1 here to create a north or a south, depending on if you've got souths all 4 coming into the middle, you get a south beam out of here. If you've got norths all pointing into the middle, and you don't have something on this side of the cube, let's say, then you have what did I say? If they're all north pointing in, you get a north. If they're all south pointing in and nothing on this side, you get a south. And you can put an electromagnet on this side, and you can have a flexible pulse of magnetic energy coming out or in, whichever way it's going. But essentially, they would look the same in terms of their structure, you effectively end up with a express pole. The primer fields is essentially taking that to the max and removing a little bit of the magnet in the center here. So you can push through where your back magnet would normally be, and then it gets affected by the pseudo-magnetic monopole. It's not a real monopole. It's kind of like a suppressed one pole. Anyway, so there we go. But even though it is a pseudo-pole, it ends up with a very strong thing in the middle, and that's that. So, now I'm talking about something a little different. So let me just get my thoughts together here, and I might speak to you. What am I doing? Okay. Okay, so I have a little bit of a story here as to how I came about to find the dead ringer. I gave an overview of it, but basically what am I talking about? I'm talking about not that. I'm talking about this. I'm talking about this. This is what I call the dead ringer. But this one for me, which is on our sample over here, this one absolutely could not be machined by John Hutchison. And as it is identical essentially in all form to the one over here, I therefore conclude that this is a genuine structure that was created by this technology. Okay, so that being said, why did I look at this video? And this is why. This is a fascinating story in its own right. So we're taking a different tack here. So the Baroness, Princess Carla Nipton Hutchison, his worthiness, he said blah 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 about the video. Check out Mercury. Find an old Mercury switch used in thermostats. Shake it hard in the dark or by a radio receiver. It will light up, and you can also hear it on radio AM band in a quiet spot. And then I say, well, we have a massive Mercury switch in Santa Cruz, which can do like 10,000 amps and a lot of volts. We'll look into that. Thanks for sharing, although you can't see the Mercury inside. As ever, your insights are so valuable. And then Mercury's interesting stuff. Very electrically active, used in clay pots long ago for don't know what. But shaken, it will glow in the dark and also produce radio waves, tight molecule atoms, sliding, producing static. Okay? Now, notice this, molecule atoms. Molecule atoms. We'll come to that right at the end. Okay? This phenomena was called a barometric light effect, and it was first discovered in 1675. 1675! All very interesting stuff indeed. Why don't we take a look at what that is? So, just for the record, it was this video, Something Electric Part 1, and you can see the comments here when they pop up. Maybe, maybe not. They're there. Okay, so this is barometric light. Okay. Let me see over here. Okay, so barometric light. Barometric light is a name for light that is emitted by mercury-filled barometer tube when the tube is shaken. The discovery of this phenomenon in 1675 revealed the possibility of electric lighting. Is that all you get out of it? The earliest barometers were simply glass tubes that were closed in one end and filled with mercury. The tube was then inverted, blah, 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 blah. Barometric light was first observed in 1675 by French astronomer Jean Picard. Jean Picard, I mean, I don't know if John knows this, but this is just fantastic. Being such a Trekkie, this will be fantastic. Jean Picard. Towards the year 1676, Monsieur Picard was transporting his barometer from observatory to Port St. Michael during the night when he noticed a light in part of the tube where the Mercury was moving. This phenomenon, having surprised him, he immediately reported it to the Scardens, or whatever that. Okay. Anyway, the point is, this is giving you a clue as to how compact fluorescents work with the Mercury. But anyway, I'm going to just do something here. I'm going to do radio. No, I don't see any radio references. I'm going to say frequency. No, I don't see any frequency references. How about RF? Oh, there's some RF there. What is that? Surface, surfaces, performed. Okay, so there's no RF. I think that's about it, really. Can you believe it? In 345 years, did no one notice it produces RF except for John Hutchison, who puts it as a throwaway comment? Did no one notice it? I can't believe it. I can't believe it. So, this is Jean Picard, and you might find it's interesting that he studied at the Jesuit College Royal Henry le Grand. Okay, so there we go, and blah blah blah. He made some instruments, and he was quite a good guy in terms of what he did. And it says here, just for those that are concerned, for the fictional Star Trek, the Next Generation character, see Jean-Luc Picard. Okay, so it's not the same guy. Okay, now. When I was looking at maybe trying to get a picture of what this barometric light looks like, I kind of went down to the references here, and I found a reference, and I came across this site. It's called the UCLA Putterman Research Group. Why is this interesting? You're not going to believe it. Why is this interesting? Right. Mysteries of energy focusing phenomenon. Right, okay, can we get it to stop? Can we get it to stop? Is it going to stop it for us? No, it's not going to stop, is it? Is it going to stop? Yes, it's all very fancy. Anyway, mysteries of the energy focusing phenomenon. We study the fate of energy that is injected into a system so as to push it far from equilibrium. A sound wave passing through a fluid can create, it's probably a little small for you. Let me see if I can zoom in there a little. Let me do that. Yeah. Okay. Ugh. Oh, I hate some responsive sites. Can I do it manually here? No. There we go. Okay. A sound wave passing through a fluid can create a bubble that pulsates so strongly that it becomes a dense plasma that emits flashes of light only trillionths of a second long. When Scotch tape is peeled from its roll in a dark closet, a mysterious glow can be seen. Somehow, the force of peeling a complex network of polymers generates a charge separation, which then organizes to create a discharge and emit photons and with energies that can extend into the X-ray portion of the electromagnetic spectrum. When a ferroelectric crystal such as lithium noebiate is heated, the ions move ever so slightly relative to their electron clouds to create massive electric fields that are capable of generating nuclear fusion in a system the size of a walnut. In these off-equilibrium systems, nonlinear processes dominate the motion. Although entropy always increases in these phenomena, the second law of thermodynamics gives little guidance in the understanding of how they work. The second law of thermodynamics gives little guidance in understanding how they work. As you marvel at the wide range of phenomena on this webpage, please wonder whether there is a new guiding principle which explains why so many different off-equilibrium systems like to concentrate energy density. The limits of energy focusing that can be achieved off equilibrium are not known. Can a similar multi-scale system someday be used as a fusion reactor? I think it can. I think it can, Mr. UCLA, that's been publishing papers since the 1988. Yes, I think it can. And you know what that is? Well, it was published in the book Evie, A Tale of Discovery in 1986. 1986! And it's all the same thing. It's all the same thing. Why have you not heard of exotic vacuum objects that literally describe everything you've said there? Everything you've said there. Why not? Why have you not heard of it? Why is Ken Shoulders not all over that page? Why? Why is he not all over that page? Why is John Hutchison, who shows, can a similar multi-scale system someday be used for a fusion reactor? Perhaps you should have gone a little bit up the coast and said, hello, John. How's that reactor coming along? Okay, let's have a look at some of these things. Sonoluminescence, okay? Okay, let's go and have a look at sonoluminescence. What have we got? Oh, dear. Oh, dear. So they got a nice video here. You can go and have a look at it in your own time, but it shows the bubble growing and then the flash of light. You see it. Whoop. Okay, so there's your sonoluminescence. The energy of a sound wave in a fluid can concentrate by 12 orders of magnitude to create flashes of light that can be shorter than 50 picoseconds. A picosecond is a millionth of a second. The flashes originate from hot spots that form inside bubbles that nucleate, expand, and crash in response to the travelling sound wave. The travelling sound wave. Sound familiar? We have observed hotspots as small as 10 nanometers and as large as 100 microns. Wow, these things can be quantized. We can generate them one shake at a time by shaking water in a vacuum flask or at a rep rate of 10 million times a second. 10 million times a second. What would that be? Sounds like microwaves. Will the degree of energy focusing that can be achieved with the physics of sonoluminescence someday reach to thermonuclear fusion? I wonder if it can. Let me think. In the movie above, a cavitating bubble is illuminated with a floodlight that is shining directly into the camera. Nevertheless, the flash of sonoluminescence is easily seen as the bubble reaches its minimum. And they've got a whole bunch of different sonoluminescence experiments on here, so you can really knock yourself out with that. Yeah, lots and lots and lots of variations here. Acoustic horn. There we go. It's a horn with the bubble on it. Sonoluminescence from a few millimeter tip vibrating at 30 hertz. 30 kilohertz, okay? That's kind of the things that we're running our ultra experiments at. The wavelength of sound is larger than the spherical tip. This device is used for ultrasound assisted lipectomy. There we go. Bubble jetting, where we know what that is. Cavitating and microstreaming, and so forth. Flow-induced cavitation. Yeah, so look, flow-induced cavitation. I was saying to you that I think it's Japanese or Malaysian or Indian, maybe, that they were using flow through a water pipe and they were getting transmuted material by just flowing water through this series of pipes. Here we go, flow-induced cavitation. I said it was because of cavitation. Now, they're not saying it transmutes matter, but they are saying maybe one day fusion will be able to be possible with it. It's been happening since water's been on this planet. Multi-bubble sonoluminescence. Oh god. Okay. All right. Well, let me go and have. They say here, like, I like this. Sonoluminescence in the early years. Early priorities for sonoluminescence included Dazzler Comics and Exodus, blah, blah, blah. See our publications. So they have publications since 91 there, Nature. And here it says, streak photo in Pearson's book showing that an explosion in nitromethane originates from a light-emitting bubble. This is why Kirk MacDonald says that all Nobel Prizes are due to sonoluminescence. Why? Because I guess this is where dynamite came from, and Alfred Nobel, as far as I'm aware, invented dynamite, and so that's where he got his money, and so he produced the Nobel Prize. And then there's something here, maybe this is in the Kabbalah, I don't know, it's the Jewish text, I think. I think it says, the sounds saw the people and all. There we go. And they've got some beautiful images here on how the pistol shrimp produces a cavitation bubble. Maybe I can show that here. You can see the collapsing cavitation bubble here, and then the flash. They do it, and that produces the pistol shrimp attack, and so on. Okay, so that is sonoluminescence. Let's have a look at the next one, and this is great. I love this. Crystallic fusion. And this is hilarious because we used to have a poster up, which is here. This poster here. Well, it's not the poster, but it's where Buzz is telling Woody that crystallic fusion. He's like, haven't they invented crystallic fusion? Well, this is basically it. Mystery of material science. A freshly made crystal of lithium niobate has an electric field of 15 megavolts per centimeter. It's saying here, apparatus to generate and detect nuclear fusion. A crystal that is only 10 cc in volume can be used to produce nuclear fusion on command. Lithium tantalate is a pyroelectric crystal which produces more than 10,000 volts. So the pyroelectric, that is what zinc oxide is. That was the subject of our last presentation in part. 100,000 volts when heated to warm room temperature from freezing. This field is focused by a tungsten tip, there we go, tungsten tip, mounted on the crystal so that it dissociates, ionizes, and then accelerates a beam of deuterium ions, proton and neutron pairs, just in case you didn't know, guys, to about 1% of the speed of light. When two deuterium nuclei collide at this speed, they can generate nuclear fusion and release a neutron with energy that is about 10 times greater than the kinetic energy of the colliding particles. There we go. So that's our crystallic fusion. And then the next one is just lovely. This is just lovely. It's just absolutely beautiful. Turbulence. Turbulence. Okay, let's have a look. Turbulence. Now, you're going to love what it says here. You're just going to absolutely love it. You're going to love it. Solitary waves. Solitary waves. And turbulence. Mysteries of fluid motion. Turbulence is a phenomenon whereby a fluid responds to the uniform input of a large amount of energy. As fluid tries to convert all of this mechanical energy into heat, it sets up complex wave and vortex motions. Although it may appear mostly random to the eye, the motion has many coherent structures. Many coherent structures. And dissipation can be concentrated into localized regions, which is called intermittency. The interplay between entropy production, randomization, and the formation of structures constitutes the unsolved problem of turbulence. Researchers agree that the basic physics is contained in the Navier-Stokes equations. Yet, the solution of these nonlinear equations for turbulent motions remains an abiding issue. Shown here is the turbulence ripple motion on surface water. At low amplitude of vertical vibration, the motion of the surface is almost regular and looks like a standing wave. At high amplitude, the overall surface motion becomes more random and the energy is distributed over many lengths and timescales. But as shown in the color image on the right, dissipation is focused into smaller regions. Now listen to what it says here. I'm going to zoom in some more because I like this. Imaging intermittency in a ripple wave turbulence. This is what you get in this. This is what you get when we don't put enough water into our ultra tank and we overdrive it. The dynamics of fluid filled with high amplitude ripples was studied with a technique diffusing light photography. This resolves the height at all locations instantaneously. Even when non-linearities are strong enough to generate motion with many frequencies, the resulting turbulent state contains large, coherent spatial structures. The appearance of these structures in thermal equilibrium state with the same average energy would be highly improbable. And then they have some solitary waves. And here is an example of solitary waves. So basically, you can see it over here, and then the solitary wave comes up. and it gets higher, and it gets higher, and it gets higher, and it gets really, really, really high. So this is what I'm saying is happening in John Hutchison's material. You are getting some solitons in there forming, and they are obviously not water, but they are a fluid of some type. Okay, so you can go and have a look at that in your own time. Yeah, and then yeah, that's that. And then the triboelectric effect. Basically, all of these things are explained by charge separation. They get that right. But what happens in charge separation, and Ken Shoulders went over and over and tried to get people to listen, is that you get electronic structures forming at electronic speeds. And you get exotic vacuum objects. That was his final name for them. Of course, in the case of Ken Shoulders, he didn't specifically define what they ended up as, but that they could be a wide range of shapes and sizes, okay, and quantization levels. The case of Takaaki Matsumoto, he very, very specifically said from the outset that they were positrons, electrons, and neutrinos in the shell, and then the ions were somewhere else, probably in the middle. But anyway, all of these things here that are on this page are essentially exotic vacuum objects or coherent matter. And they're saying it's far from stability, you know, it's highly dynamic, but actually like extremely off equilibrium. I'm saying that the bits that are these very intense things are coherent. They're saying that too, but the whole thing becomes coherent matter. Okay, so we can get rid of those now. And you can go and have a look at that in your own time. So they do have one paper here that's a little bit earlier by Putterman, but this is in 1984. So this is 5 years after John was doing his stuff. And it was submitted on the 25th of April, received 25th of April 1984. And it's talking about non-propagating surface wave solutions. And you have like a soliton here with your very high peak and your low bit. Now the thing is, they've used super duper duper fancy imaging technology, and we're using a sheet of kitchen foil. And the great thing is, you actually see in the kitchen foil after you've finished what it's done. Oh dear. So the reason I ended up on that Putnam site is because they had done this paper, like you see Putnam here, okay, of showing, and I wanted to have a photo of what this Mercury looks like. So this is a glow from Mercury. Can you see that? Can everyone see that? No, that's not. It's growing the wrong bit. Let me grow this. Okay. There we go. So this is the meniscus around the Mercury with your glass vessel, and this is the glowing edge that you've got there. Okay. And this is in Nature. There's quite a few of these papers you're going to see tonight they're in Nature in January 1998. Okay. So only 323 years after it was discovered. Okay, let's just see if they had discovered the RF. Let's see if they found the RF. Okay, let's go. Radio. No, there's no radio. Medium wave. No. RF. Should get some RFs because it's in words. No RF, 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 no RF. No, 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 no. No RF. One of the leading groups, the paper in Nature, doesn't mention that it produces RF. John Hutchison gives a throwaway comment on a YouTube video. Oh yeah, produces RF. Of course it would do. It would do, because it's producing exotic vacuum objects. It's producing exotic vacuum objects. Itonic clusters, ball lightning, micro ball lightning, ectons, you name it. But it's all the same thing. And they're either forming and producing UV up to 2 keV, and the UV might be exciting vapors of the mercury and causing a glow, or their theory is that you get electrons stuck to the glass, and as the mercury pulls away, you have like positive ions over here, electrons over here, and you just get an acceleration. It's just the electrons that are exciting the gas as they move through to rejoin the ions on the other side as charge separation. No, it's forming clusters. It's forming clusters. And we know that because John gave a throwaway comment. John Hutchison gave a throwaway comment. Oh yeah, it produces RF. If it's producing RF, then it's producing EVOs, either on the formation. Sorry, when they blow up, they produce a pulse of RF. And if it is a spark that goes from the glass to the thing, every spark has an EVO in front of it. So whatever way you look at it, it's got EVOs. What does that mean? It means we can transmute matter. Okay. Is there anything else I wanted to show on here? Oh yes, and in another one, in a paper in 1987, they're talking about creating solitons in metal. There we go, solitons in metal. I rest my case. Okay, all right, let's get back to the main presentation. Before we go on, are there any questions? Any questions? Do we have any questions? I wish I brought some water now, I'm thirsty. Mercury was used by the alchemists to produce gold. Yes, well, we'll deal with that. That's the question that I've been hounded by so many people, and I've already written a whole blog on it. But anyway, we'll nail it today. Would like to see the SEM of aluminium going to carbon. Is that available, Bob? Yes, I will put... Okay, so after this weekend, I'll backfill the other presentations. I was going to backfill the other presentations, and then this came up. So I had to kind of fit this in before I do the second part of something electric. Okay, I'm just going to crank on. All right. Okay. So I shared this a long time ago, at the beginning or last year, and I'm not showing in this one the smaller structure, which has a radius of 50 microns. It's 100 microns overall, but this structure here at 200 radius, which is 400, And if you actually look at this, it has a hexagon on it, but unfortunately the red line's in there. You can see the point down here and a point over here. So so this is not a base level of an EVO that I found, and this was found on this sample here, the fracture sample. In fact, all of the quanta of the EVOs that I derived this structure from came from here. But note that this is 200 micrometers across here. And if we go back to our structure, where is it? Up here. That's 200 micrometers radius, so it's 400 micrometers, and that's the same structure as this one. And I would expect that this was probably, their one was either the quanta below, it's probably the quanta below, but this one is the same size as the one on the fracture sample. So the fracture sample is actually from 2007, and it has the same scale exotic vacuum object mark as the Ballburn sample from 1986. So whatever we say about this process is definitely able to be repeated. It's definitely able to be repeated. Okay, so yeah, so this is the mid-level structure, and then the next one takes those 400 micron disks and creates a larger structure, but they are pinched on the inside. So they get pinched on the inside and they get larger, so as it sweeps down. Remember I showed you the sweeping in the inside of the this structure here. So if we go here and I pause there, you can see these scallops and these scallops going in, the scallops going in. So it's the same thing, and in fact this actually is one of these kind of like question mark shapes. It has a bit that's eaten out over here. You can't see it so clearly there. Maybe it's on the other one. Maybe you can see it clearer on this. It comes out here. You can see there's a little kink here. So this is essentially the same kind of thing, but at a slightly different angle, as we've seen before. Okay, so yeah, this is the larger quanta, which we've seen here. So this is a smaller quanta. Then these go around here to make this one, which is 400 microns across. And then this is 400 microns across, and these group round. But they have to pinch on the inside because they have less space coming out. And here you can see roughly from a top view. They can get distorted. Anyway, you can see this is an angle which is similar to the other one. And I have here I think this is the one. Yeah, you can see the ridges here. So there's a ridge and then there's a gap. There's a ridge and then there's a gap. There's a ridge and then there's a gap. So either these things are, how shall we put it? They're attracted, but they are repelled. They are attracted and repelled, but the structure itself is able to eat the aluminium or move to make a dent in it. But it affects less in the gap. So there's two different types, very different types of things that are interacting with the aluminum here. Okay. And so I derived in the video that I had at the beginning there, 17th of February 2020, that this is one example of the structure. So you have the smallest quanta here, which is your, whatever it was, your 100 micron one across, and there's a smaller one by the way. Anyway, 100 micron, and then your next quanta up is this, and that is the larger one, which is this overall size one, which has got the lump in the middle. I've got this at a different angle, and you can see this is a spike coming up, a thin spike with a curve. Anyway, so that's that. And then these link together to go like this. And with this 3-level one, you have the pole here, but then you have the pole here, and then you have the pole inside, which effectively can go across the top and down round the bottom. So these things don't move. They are fixed in place. Okay, and it's this curved bit here that leads you to have these scalloped out sections here. These scalloped out sections. Okay. So they are interacting with the material differently between the ridge and the other part. And that is the same thing that you're seeing here, but not in this one, in this one here. It's the same thing you're seeing here. There's scallop here. Interestingly, this has less scallops in it. So I think it's maybe got per side, or you've got 1, 2, 3, 1, 2, 3. So it maybe has 3, 6, 9, 18. This has less in the core. You can kind of work these out, and I think that the one right at the top here, it's got less, even less rather. 1, 2, 3, and if you say 4, 5, 6, 7, 8, 9, 10, 11, 12, probably 12 in here, something like that. But the one that we are looking at here is from counting these ridges, and for a quarter turn, I derived that it had 48 around it. And so that is the structure here. Now, the substructures themselves don't need to have 48. So I've got 48 around here, and I've also got 48 around there. Okay, so it doesn't need to have that many. You could have 3. In fact, you can have 2. On the line, we've seen 2. And 2 is the minimum to make a ring. Okay, and they have this D4D structure. So by that I mean the diameter of this section here is 1/4 of the diameter of the overall diameter of the structure, and so this is D, and then you can fit 4 of them across. Okay, so, but this diameter is the diameter of the substructure here, and then if you group those together, you get that. So it's always that kind of pattern. Okay. Now these things can break and they can come out and so on. They are linked. Now, are they linked gravitationally or are they linked magnetically? Are they linked gravitationally or are they linked magnetically? And these things these are flexible. We know they're flexible because we can see they're flexible. they're springy loops. Okay, they like in free air, and ideally they would like to be at equilibrium and they would form a ring, but they can, as it crashed into here and interacted with the material, it's not quite perfect ring in this case. I would imagine that the less levels of subdivision they had, so like the smaller units have less opportunity for deformation. Okay, and I think what you can get is these grouping into very, very large structures. Anyway, so why? Josh Hannon sent me a paper yesterday, and I found this absolutely amazing, absolutely amazing. This paper was written in 1954. 1954. And here it is. This is John Archibald Wheeler, and it's called Geons. The Palmer Physical Laboratory of Princeton University, Princeton, New Jersey. And this was in Physical Review, volume 97, number 2, January the 15th, 1955. This was published. This was published in 1955. Regions of strong electric field strength in a simple toroidal geon of zero angular momentum. Zero angular momentum. Okay, so they're implying that this structure is not going round itself. What did I derive? This is not going round itself. It's fixed in place. That enables it to carve these structures in this material. Okay, it enables it to carve these structures because the structure isn't rotating around. It can shift material around it. How can it do that? Because it's shifting material between this layer, and then that is passing it on, and it shifts around, but this is not moving. With strength in a simple toroidal geon of zero angular momentum. 2 waves of equal strength run around the torus in opposite directions. So you've got a wave running around this way, and you've got a wave running around the other direction. Okay? And they produce what do they produce? A standing wave. Okay? They produce a standing wave with electric fields strong in the region indicated. So in here, in these little discs, in these little disks, there is a very strong electric field. Okay? And magnetic fields strong in the region between. Magnetic fields strong in this period in between. Magnetic field strong in between. Magnetic strong in between. Electric field strong here. Magnetic field strong in between. The gravitational field created by this disturbance, and required to hold the disturbance together, so this can only be held together, is represented to a good approximation as a static and independent azimuth. Okay, here. So, let's go and have a look at this paper. Give me a second, I will find it. I have it here. Firstly, I will go to that slide again because so just to go back to that slide. Just look at this. It's saying the gravitational field created by this disturbance and required to hold the disturbance together is representable to a good approximation as a static and independent azimuth. So it's saying there is a gravitational azimuth. As far as I can understand, it's this point that's represented. Static gravitational azimuth here. And that holds this structure together. Is this electrogravity? Is this electrogravity? Is this the core of electrogravitic technology? Is it? Is it? This was, how did he get to this? How did he get to this? Let's find out. I'm going to do what most researchers do and just read the conclusion. I haven't read much of this paper, but I read enough. Conclusion. Taking seriously, i.e. paying attention to, taking seriously and following out the consequences of the 40-year-old theory of general relativity, we have been led to recognize the relative stability of certain types of electromagnetic field disturbances held together by gravitational forces. Held together by gravitational forces. What did Takaaki Matsumoto say in 1989? He said that you get structures called itonic clusters, and he said they were made of electrons, positrons, and neutrinos, and that these could take ions and cause gravity collapse. Gravity collapse. If you can imagine something which is a mesh of structures like this, that have a gravitational field, that if they get so intense, firstly, they're churning the material, and secondly, they can maybe get so much material in there with and it's building strength, and it's building strength, and it's building strength, and it's building strength, that it causes gravity collapse. But also, one might think that if this was skinning a subject, or there was a superstructure of this that had a gravitational vector in one direction, then it would cause something to lose mass. It would cause something to lose its expressed mass when it's relative to another gravitational body. Okay. On entry into the quantum domain of sizes, electromagnetic geons build up field strength strong enough to produce pairs of electrons. These things can invoke pairs of electrons. Okay? Now, I imagine they're saying electron-positron pairs, not just straight pairs of electrons. Okay? But if they're positive or negative, whatever. Matsumoto in 1989 is saying that a itonic cluster is made of positrons and electrons and neutrinos, meaning neutrinos and antineutrinos. Okay, they're saying in 1954 and published in January the 15th, 1955, that these electromagnetic structures, almost word for word or design exactly based on observations. I derived it from physical evidence. And they have derived it from Einstein's general relativity equations. At not very different sizes, neutrino geons commence to give birth to mu-meson electron pairs. So if you get a different size of these structures, you will get it creating mu-meson electron pairs, muons. Okay? One interest in the following geon theory down into the quantum domain will depend upon one's considered view of the relation between very small geons and elementary particles. So they're kind of saying, potentially, this is how it goes all the way down. And we know that we can make, if you look at the beginning of the presentation, we can make them 400 microns across, and we can make them big, like my hand. And I'm pretty certain we can make these the size of galaxies. As above, so below. Okay. So you really should read this, because in addition to purely electromagnetic geons, there consequently also exist in principle purely neutrino geons and geons of mixed type. Thus half integral as well as integral spins are permitted to geons. Now I have said, sorry, it's this bit that I'm looking at. Now I've said for years that Shishkin et al. At Dubna at Science City say that neutral strange radiation, as they observe coming from a wide range of equipment, from cavitators through gamma sources, through brush discharges or corona filament discharges or corona discharges or electric field plates, you name it. They get these birdies, these 50% mushroom shapes, which I believe is what we're seeing and observing, but they're smaller quanta. They're not the size that John Hutchison were making. These are kind of like the very small quanta. They're the sort of ones that would make up into something much bigger. They're saying that these are formed in these devices, but they become neutral. And the ones that they interact other material with, because they can cause beta decay, they are comprised of potentially a cluster of cold neutrinos, i.e. relic neutrino type neutrinos, but these are synthesized neutrinos. Now this paper from 1954 says that electrons in a geon, or whatever, light particles in the geon can synthesize this, electrons can synthesize neutrinos, neutrinos can synthesize electrons, exactly how I felt it's been for years. And like everything, nothing is new. Nothing is new. You just have to look at the literature. Like this guy did. He took seriously what Albert Einstein had said in 40 years earlier, and found you got these very stable structures which were held together gravitationally, and they had intense electric fields and intense magnetic fields. So if you read this paper through, you will see that they are saying, maybe I can see it here, that's just fine. I'm trying to avoid any equations, but I think I did promise I wouldn't do any equations, but maybe I'll just have to speak it out. Where is it? Where is it? Where is it? Now, bearing in mind, this was written a year or two before the neutrino was actually observed. So, anyway. Let me see what I can find here. So they're saying that neutrino and antineutrino can go to a muon and an electron. So you can get that. That is going to be very, very important on Sunday, that equation. What am I showing you? I'm showing you this one here. Neutrino, and I believe that's an antineutrino. It's not necessarily the right nomenclature for it. Anyway, goes to, I assume that's a muon and an electron. Okay? And if we can find it, he's got neutrinos in here like so many times, it's not even funny, but let's see if we can find the references I'm referring to. If I could spell neutrinos, that would be helpful. However, if real production of muon and electron pairs sets the only limit, then it's possible in principle to treat in terms of existing theories objects built up solely here. Then it is possible, in principle, to treat in terms of existing theory objects built up solely of neutrinos and gravitational forces. Solely of neutrinos and gravitational forces. You can have something that's neutral, is a stable structure, and has a gravitational force. This lower limit for pure neutrinos, okay, so let's go on. I just want to show you that you can switch between neutrinos and other structures within these structures. Okay, so the consequences are the existence of the neutrino antineutrino to muon to electron reaction at high energies, and neutrino and antineutrino scattering at low energies. Anyway, I'm going to read this whole paper through before Sunday, and I would recommend everyone else does. And I want to thank Josh Hennon for highlighting it. I don't know what he did an reverse image search, and I don't know whether he found it because of this structure or because of this structure. Not that one. Sorry, too many equations. This is showing here. Look. So he's talking about here, photon-photon collisions provide one of the mechanisms for escape of energy from the active region of a geon. The same mechanism is describable from the wave point of view in terms of a coupling between otherwise independent modes of oscillations and electromagnetic field. The two sources of nonlinear coupling are virtual pair phenomenon and non-static parts of the gravitational field. So he is saying that energy can be lost from a geon by photon collisions and them coming out. How does a exotic vacuum object perform when it is getting electrons or it's getting material? It's shedding energy via typically photons. Okay, so if the nuclei in there are being condensed and they're emitting lots and lots of photons, the photons are all whisked up into this structure as well, because it's got such a high gravitational field, whatever, that light can't escape. We can see this in the Bogdanovich. You can see these toroids in the Bogdanovich experiment, where you've got plasma flow discharge behind, a plasma discharge behind, and the light doesn't go through the torus. It doesn't go through. So it's able to stop light. Now, is it capturing the light? I think it probably is. Anyway, so my point being is that they're describing how it can lose energy through photon emission. Okay? You can't patent this. You cannot patent this. You cannot patent this. Okay, so he has here neutrino-containing geons. There is little difference between the theory of geon built out of neutrinos and one built out of electromagnetic fields, apart from the fact that each neutrino state will accommodate only one quantum of energy. The general relativity, blah, blah, blah. The modes of dissipation of energy are still leakage through the refractive index barrier, coupling through nonlinear effects to waves that run freely to infinity. That would be a long-range effect. And various forms of fission. Okay. Consequently, there is little point to reformulating the in terms of neutrinos our discussion of the properties of electromagnetic geons. But having said that, he goes on a lot about this. One difference appears in the process of interpenetration of two geons. When both are made of neutrinos, the overlap of the active regions of the two objects will force a promotion of their constituent neutrinos to states of higher momentum and energy in accordance with the Pauli principle. The uptake of energy implies a strong effective repulsion compared with forces that would otherwise have been at work, as for example in the collision of electromagnetic geon and a neutrino geon, or the impact of a neutrino geon on an anti-neutrino geon. So they are saying that you can make a whole new geon out of neutrinos and a whole geon out of antineutrinos. Thus, there is a certain interesting specificity about interaction of geons. Anyway, the point is this: is that John Hutchison absolutely nailed how this works, and everything John Hutchison has shown on camera is real. Deal with it. Deal with it. It's real. Okay? And I derived it from physical evidence on this sample long before I ever read this paper. Okay, so then I want to share with you something that was shared with me a few hours back. And bearing in mind what John Hutchison said earlier here. So John Hutchison said, Mercury is interesting stuff. Very electrically active, used in clay pots and blah, blah, blah. But shaking it will glow in the dark and also produce radio waves type. Molecule atoms sliding produce static. Molecules. Right. Now, what did Ken Shoulders use in his patent? His preferred electrode. It was a wetted electrode. The wetted electrode used mercury. Why? It's heavy, it's already a liquid, and a heavy ion will produce a stable EVO. Guess what? In the 1930s, it was Tesla also that used mercury in his death ray. This is not a coincidence. Molecules, atoms sliding. Okay, now. This is from today, and thank you to Nick Moore for sharing it. Physicists harness thousands of molecules into a single quantum state. Really? Well done. Science alert, tiny blah blah blah. Transition from an atomic to a molecular Bose-Einstein condensate in Nature, published the 28th of April 2021. What have we got here? Oh, have we got a D4D structure, which is a hexagon? Have we? Have we got a hexagonal D4D structure with little round blobbies on the way round? I think we probably have. But because it's so small and so low res, You're fighting to see it, but it's there. You got the curved bit here, you got the curved bit here. If this went into some steel and it was made in a little bit more energetically, you'd see something like we showed at the beginning of this presentation. You'd see something like this. This is a very big one. This is a very big one. This is 400 microns across. This is very, very big. This is like size of your hand stuff, okay? This is really, really small. Let me get the paper up. Actually, there isn't a paper, but I do want to read you. The paper's not available through means. Let's put it like that. Okay. Okay, it's quite a nice little article, and it's got the image on the top there. So here's the article on Science Alert. So there's our hexagonal D4D structure with little balls in it. Okay, physicists harness thousands of molecules into a single quantum state. In a major milestone for quantum physics, thousands of molecules have been induced to share the same quantum state, dancing together in unison like one huge supermolecule. 1979, 89, 99, 2009, 2019. Oh yeah, that's 42 years after John. Well done for your amazing thing published in Nature. People have been trying to do this for decades. Yeah, well, that's because they weren't listening to Ken Shoulders, and they weren't listening to John Hutchison, and they weren't listening to Takaaki Matsumoto. They weren't. So we're very excited. Sorry, said physicist Cheng Chin from University of Chicago. I hope this can open new fields in many-body quantum chemistry. There's evidence that there are a lot of discoveries waiting out there. Yes, the evidence is in John Hutchison's work, and the evidence is in Ken Shoulders' work, and the evidence is in Takaaki Matsumoto's work, and Sviatomenko's work, and Leclerc's work, and Mars's work, and Piantelli's work, and yes, there's a lot of evidence. Nature, well done, well done. Oh my God, are they going to have a rude awakening when they realise that for decades they have been stifling the root technology? They're willing to publish papers that hint at the possibility of quantum effects being available on the macro level, yet they're not willing to look at John Hutchison, who's actually showing it in 1979. He's actually showing macro level quantum interactions. The concept of many particles acting together as one big particle sharing their quantum states is not a new one. Well, at least you understand that. We've achieved it and experimented with it for decades with clouds of single atoms in a state of matter called a Bose-Einstein condensate. These are formed from atoms cooled to just a fraction above absolute zero, or any temperature you like when you have macro ball lightning, but not reaching absolute zero, at which point atoms stop moving. This causes them to sink to their lowest energy state, moving extremely slowly so that their energy differences disappear, leading them to overlap in quantum supposition. The result is high-density cloud of atoms that acts like one superatom or matter wave. Matter wave. This is coherent matter wave technology. John Hutchison nailed it. Ken Shoulders spent 33 years trying to get to the bottom of it. He didn't do that because he was dim. We can only speak because he was the father of microelectronics. We can only analyze things because he invented the quadrupole mass spectrometer. He was not dim. Molecules, however, are made up of multiple atoms, bound together, and therefore a lot more difficult to attain in this way. No, sorry, already been done. Atoms are simple spherical objects, whereas molecules can vibrate, rotate, carry small magnets. Because molecules can do so many different things, it makes them more useful and at the same time much harder to control. To create their molecular Bose-Einstein condensate, the team led by physicist Zhendong Zhang from the University of Chicago started with an atomic Bose-Einstein condensate using a gas of 60,000 cesium atoms. Why cesium? Because it's 133. It's all the same nuclei. That's going to make it easier to make our coherent matter wave. Next, they cooled the condensate cooled it even further and ramped the magnetic field so that around 15% of the cesium atoms collided and bound together in pairs to form dicesium molecules. Like, I don't know, what else does that? Oh, could it be gallium? And what else does that? Oh, yeah, because like Mercury likes to form actually ion, but dimers of ions. I think it's Hg2 double plus, but that's a molecule. Okay. Gradient was the unbound atoms were ejected from a trap, and the magnetic field gradient was. This sounds really complicated, doesn't it? Really sounds complicated. Levitate constant. Blah, blah. Typically, molecules want to move in all directions, and if you allow that, they are much less stable. We confined the molecules so that they're only on a 2D surface and can only move in two directions. The resulting gas was made up of molecules that the scientists found were all occupying the same quantum state, with the same spins, orientation, and vibration. We're yet to explore what a molecular Bose-Einstein condensate can do. Okay. Well, this is a significant step in that direction and providing an empty canvas for future experiments. Not just for molecular condensate itself either, but for the transition between atomic and molecular... Oh dear. The team's research has been published in Nature. John's work should have been published in Nature in the 1980s. Now why have I gone through this extremely circuitous route to get to my last few slides here? Well, you're going to find out. And it's this. Cardone is an Italian. He works with a team. And if you go to this video, you will see them. And they've done a whole series of experiments where they use an ultrasonic horn, which has a cone which focuses the sound so that it's extremely intense, so you get far from equilibrium, okay? Far from equilibrium, which leads to coherence, bizarrely, okay? Which leads to coherence, bizarrely. And they've got some mercury in the bottom here. And what happens? They get transmutation. They get all kinds of transmutation, okay? Why? Why are they getting transmutation? Because charge separation, just like as in sonofusion, which Ken Shoulders said is charge separation, it will therefore produce EVOs. And that's why you get a flash. Okay? Then you have cavitation in the mercury. Now we already know that if we have charge separation in a mercury, from what John Hutchison gave as a throwaway comment, that with at least 20 minutes to 30 minutes of looking online, I couldn't find on Wikipedia or some of the leading authors that they had observed the RF. I'm sure someone's done it. I'm sure someone's observed it, but they don't know the significance. The significance of that RF, whether it's coming from a spark, which always has an EVO at the front, or it's an EVO and it's exploding, whichever way, it's an EVO that's exploding. It means there is EVOs in that. You know what? You can get mercury to transmute by going. That's all you need to do. It'll transmute. You just shake it. If you shake water in a vacuum glass, you'll get cavitation. Roy Shinamaza was shaking water and getting every element in the periodic table. So what I'm saying is the cavitation in there, as observed repeatedly, an easy repeatable experiment using Mercury, he's getting transmutation. Now, you have the mechanism. It is exotic vacuum objects. You know this because you can't shake Mercury and not get charge separation. And when that occurs, you have Hg2++, and you have electrons. Two electrons ripe for making a Cooper pair. Cooper pairs like to join together, don't they? You've got a really good scenario for making an electron-bound EVO. And what do you want? Well, you ideally want Mercury. It's what Tesla was using. It's what Ken Shoulders decided to put in his patent. Why not use Mercury? You have everything you need in that experiment that you are looking there to transmute metal using an ultra experiment. Okay? Now they have a whole thing explaining warped space-time and blah, blah, blah. That might be happening. That might be happening. I mean, if you get warped space-time, you can imagine that there's some gravity going on. And, well, okay, so those little structures, those geons are making gravity. They are electro-gravitic structures, magneto-electrogravitic structures, specifically magneto-electrogravitic structures. The Russians call this magneto-toro electrical radiation, and I just added the gravitic in there because what I saw had to be involving gravity, and there we go. You've got our friend here from 1954 called John Archibald Wheeler. Nailed it in 1954. So what would I recommend? Because this is the question I get asked from a lot. Okay. I get asked, how do you make gold? How do you make gold? I don't know why so everyone's interested in becoming like goldy, like have loads of gold. It's beyond me. Anyway. What do you need? Well, you need potassium. Why do you need potassium? Because it produces the largest outcome for energy. It's 15.7 mega electron volts. Now, mercury, potassium. Now, the interesting thing is here, mercury's really toxic. Okay. Now, I want to go to my making gold experiment. Document from about 3 or 4 years ago, which I have already prepared for you here. Somewhere. Did I? Yeah, yes. So this is my Steam It blog from over 3 years ago now. Basically, when we had the first versions of the Lena reaction calculator. So basically, Alexander Parkhomov assumed that because we don't see certain types of radiation coming out of Lena, it's likely that it's 2 to 1, 1 to 2, or 2 to 2 as a base level nucleon exchanges, fission or fusion, and therefore you don't have any nucleons coming out. You've only got exchange of electrons and interactions with neutrinos. And so with Philip Power, there was the development of this database. And the first time I used this database was with a different version. Anyway, and it was produced by a different person, which I can't remember the name of. Sorry. But the one basically it took around about 50 seconds to prove that the alchemists were right in what they were using. And so from the Royal Society of Chemistry, you have these things, and on the Royal Society of Chemistry, it says, I don't know what is it? Bismuth is used for. They didn't know what bismuth is used for. Interestingly, we have our friend zinc. Okay. So this would be your thermoelectric accelerator. Okay. Your mercury here is your mercury, but I'm suggesting not to. You've got potassium here, potassium, mercury here. I would not use mercury, and I suggested to use calcium. But if you look at the elements that they didn't have, actually, thallium, which is pretty good because it would have killed them very quickly. But they had bismuth, mercury, and lead. And if you look at the different products for the various, where is it? I've got it here for bismuth. So if you're looking for bismuth and gold coming out, calcium, and potassium are your top 3 energetics, and that's 33. So that, in my view, is kind of like more than twice as energetic as this. So it's more likely to proceed, in my view, because it wants to pack it into a smaller box. Why does it want to pack it into a smaller box? Well, it's effectively a black donut or a black sphere, but it's not really. It has an event horizon, but the event horizon is where all the action is. So that is bismuth. And bismuth, what I would suggest you did is, and I don't know whether this will work, but here it is. You get a chamber, you warm it up, and you put your bismuth in there, and you put potassium. Very dangerous, very dangerous. I don't know how miscible they are. I don't know how miscible they are. Or you can use calcium, as you can see. Calcium's actually more favorable by some margin. These aren't the only outcomes, and I'll just run you through the equations on the equation calculator. So you'll see in a minute. And then just use ultrasonics, or slightly shake it, or whatever. But ultrasonics, you're going to get more cavitation and process it. Now, it might be that you certain frequencies, certain energies of frequencies, certain chamber shapes, certain temperatures of the overall mixture, certain concentrations between the potassium and the calcium and the mercury would be different. Maybe you could do it in water. So you could start with a bismuth salt, a calcium salt, and a potassium salt. I think that would probably be the way to go forward because it's less risky, and it's already in the ionic form. And you know the ions will be interacted with by the exotic vacuum objects, which I believe will form in the cavitated water. The reason, when I talk about that, it's important to look at what Roy Shinamaza did. Roy Shinamaza used a 100 Hertz vibrator when he was testing to remove the radioactive water in 2012 from Fukushima, and this is part of his proposal, and I was tipped this off by Camilla Berner. I had seen it before, and it's on coldfusionnow.org, tag Fukushima. And they're showing here that basically they had none of these elements in to begin with, and then they used this 100 Hertz vibration, and they ended up with all of these elements being synthesized: magnesium, aluminium, selenium, and so on. It helps if I'm showing you what I'm talking about. Here we go. So they've made all these elements for after 100 hours of 100 Hertz vibration and so on. And I've also already talked about the fact that they were able to remove 2 half-lives from cesium-137, tritium water, by using his vibrator as well. So it would be technically possible to. What you would have to do is, if you wanted to make gold like that, you would have to wait, right? But you could start with some bismuth salts and some potassium salts, or some bismuth salts and some calcium salts more preferentially, and you could shake those in the water. So this is for you, someone who knows Show asked me to say, what salts do I need to put in the water? Well, a calcium salt or a potassium salt, probably potassium because it's got potassium 40, which interacts with the neutral exotic vacuum object to produce beta particles, and the beta particles are very high energy, and they can energize the exotic vacuum objects in there. So that's what I would, and so you could put a mixture of potassium and calcium salts in there, and then some bismuth salts in the water, and then ultrasonically vibrate it. It might be the case that you could literally go out and get milk of magnesia, which, as far as I know, has calcium in it. Pepto-Bismol. What's in Pepto-Bismol? I know Pepto-Bismol has bismuth in it. Let's find out what Pepto-Bismol has in it. Now, the price of indium sorry, the price of mercury and bismuth is probably going to go up. Okay, so here we can see that Pepto-Bismol has bismuth. Okay, so it's got a lot of carbon in. Okay, the carbon might be a problem because it might get in the way. So maybe having a different bismuth salt might be better, but you could try it. There's no harm. Just go to the pharmacy and get some bismuth, Pepto-Bismol, and some calcium salt or something like that. Anyway, so what I'm saying with Amaza, he's moving up the periodic table. This is what happened with Leclerc. He started with water, aluminium, PVC, and that's about it. And he ended up creating every element in the periodic table all the way and well beyond heavy elements. I would be extremely cautious. Because if you push it too hard, there's a chance that you will create much heavier elements because you've basically only got bismuth in there. And there's only one way it can go. There's two ways it can go, up or down, and up is all radioactive. Okay, so there's a risk with that. So this is not necessarily for the faint-hearted. I would recommend you have at least, if it's going beyond bismuth, it's going to create potentially neutron emitters and beta emitters, definitely beta emitters. And so, but it might be that if you can get it into the EVO and you have a whole bunch of potassium or calcium ions and a whole bunch of bismuth ions, what Lena likes to do is average in the middle. Now, what I've shown you are the outcomes that yield gold. And the outcomes that yield gold the most are mercury and lead with potassium predominantly, which is interesting because they used potash, the alchemists. And potash also contains carbon, which I believe is important, and also calcium. So it has these things in there. And in the case of bismuth, the top two reactions are with calcium. And since bismuth is a single isotope, it will tend to go with the calcium. Okay, so let me just get the reaction calculator up here. And we'll get the reaction. So this is how you'd use the reaction calculator at nanosoft.co.nz, and this is the results which I've showed you before. So we go to 2 to 2 reactions on the top. Maybe I can zoom in a little bit so it's a little bit easier to see. And I'm going to swap this out for the one that I had in the presentation. So element 1 in is potassium and calcium, element 2 is mercury, and element 4 is gold. So that's what I executed, and you can see that it runs away. Philip Power's wonderful coding. Thank you very much, Philip Power, absolute legend. And we get more reactions if we haven't turned the neutrinos off. So let's just assume we're not getting any neutrino reactions, and we just get these reactions with potassium and calcium. And see the top two energetic ones. Oh, sorry, I've not got order by MeV descending. This means it shows the most energetic ones at the top. And remember, the most energetic ones are those that want to get into the smallest box. And that's what I believe that they will try to do. Okay, so yeah, so potassium with mercury leads to gold. This is why potassium was so important to the alchemists. Let's try lead in here. So remember, potassium, mercury is giving you 15.79 peak. Let's put PB in there. Now you could melt PB, or you could use a lead salt, but again, I wouldn't use lead or mercury salts. Lead, I think, is probably cheaper than bismuth, but bismuth is a lot safer. You can get it in things you drink, right? So I guess it's a lot safer. Okay. Okay, so in the case of lead, it's heavier, and so you would expect more energy yield, and sure enough you get more energy yield. But again, it's potassium, calcium, potassium. Okay, and that gives you your reaction products. And notice you'll get other reactions down here. And now I'm going to put in bismuth, and In bismuth, again, it's a heavier element. There's only one isotope, calcium, calcium, potassium, and it's a much more energy here. So it's more likely to happen. Now, I just want to show you that it isn't just these products. If I actually remove element 1 here, you will see how many products you actually get. And it's probably a very large number. It's only 127. It's not that big, actually, without neutrinos. Okay. And the interesting thing is, the most probable reaction to produce gold is calcium and potassium. So whatever. If you're saying if I don't put anything in as my element 1, the most favorable reaction is calcium to produce gold. Now, if I remove gold, so I just put in and I put back in the reaction product, the reactions feedstock that I have. So I'm going to remove gold, so I'm not forcing the outcome. And I'm going to still order by MEV, okay, descending. So in this case, I'm not saying I'm going to produce gold. So this is what is going to show you what you will produce as well as gold, okay. Element 1 in is potassium and calcium, and so these are our ingredients in our chamber. If we just got a liquid metal scenario, mercury, potassium, and calcium, okay. And I execute the query, and what do we get? 1,000 rows, and in fact it's much more than 1,000. It's much more than 1,000. But in the case of mercury, what's good is that you'll get a lot of tin, and if I actually put in it's 120 MeV, so it's like if I go down to the first gold, here, I have to go down and 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 down. It's not even on there. It's not even in the first 1,000. So there are a lot of reactions, and so actually he's put a limit on this, so it won't return more than 1,000. So maybe if I just put calcium in there to restrict it, and see if it gets less than 1,000. No, he's still 1,000. Let's see if we can see gold. Oh, gold. Gold has appeared in the table, is it? Yes. Okay. So if we only put calcium in, it's all the way down at 1,998, 997, 996, 995, 994. It's the 994th most likely product. Which is meaning it's not very likely. Okay, so let's go up and try potassium. See let's try that with bismuth. Okay, let's try bismuth. So we'll try bismuth, and we'll try let's try calcium. No, let's try potassium. Only 82 rows. Only 82 rows with potassium and bismuth. So where does gold appear in that? Gold. What are we looking? Oh, so it's 31.2. It's only 4 times more energetic to produce tin. And tellurium. Tellurium might have some value. So you might get tellurium, you get xenon. Xenon's got a lot of value. That's expensive. Tellurium, neodymium, samarium, dysphorium, erbium, ytterbium, hafnium, tungsten, osmium, platinum. Oh, there's a lot of platinum in there. We already know bismuth can become platinum just by giving it a lot of shock on its own. So there we go. So I would recommend that it be potassium and bismuth. I don't think it will be better with calcium. Maybe it will. Maybe there's less products above. Okay. There's only 70 rows. Where's the first gold row? Gold. AU. It's 126 compared to 33. It's about the same. So I would suggest either, really, but whatever's most missable in bismuth. And again, I think then it becomes what temperature, what ultrasonic energy, how long you do it for, the shape of the chamber, and the temperature of the materials. So, and that's it. So, but I mean, even if you can produce a few micrograms in a little bit of whatever, then you might be getting a very high yield relatively. Anyway, that's a bit of fun for you. So those people that can say, what do I need to do to produce gold with this? I've done it. I kind of basically told you 3 years ago, but I think people can get closer to accepting that this is exactly what is going on. There is a scientific basis that's come from absolute study of physical objects coming to a structure that is electro-gravitic, and the Russians call it magneto-toro-electro, and I add gravitic to it. And that it was calculated from, well, basically 1954. There we go. Right, so any questions? Any questions? Hey Bob, did you get my video? Yes, I did. Thank you very much. I extremely quickly stepped through it because I was in the middle of preparing the last slides for this presentation, so I will look at that in more detail. Okay, no questions. Okay, well, Gordon, I think at the end of this presentation, I wanted to give the how do you make precious metals. I kind of dealt with that in one of the previous presentations in Shockwave. So hopefully I can put to bed the people. I mean, the reality is that most people won't bother. So, but I've done it now, and I've given you a couple of approaches, and I think today it's a completely. I'm pretty sure that I could tell my children that, look, this cavitation causes this radio pop, right, from this Mercury. This person observed transmutation. This guy was able to... I think it's not going to be complicated for the next generation to understand these extremely small logic steps that are required to understand how this technology works. What shocks me is that UCLA can have a whole department that talks about all of the phenomena that are producing these effects without once mentioning Ken Shoulders, without once mentioning Takaaki Matsumoto, not once mentioning low-energy nuclear reactions or the entire cold fusion community. How is that possible? How is that? They are hiding the information, or they are willfully ignorant. It's so disappointing. It's so disappointing. So disappointing. If people make a sensible amount of gold and they want to make a donation to the project, that would be helpful. But I'm focused on making a fix for Fukushima and other radioactive sites and energy, and I think when you and then after that we can talk about other applications that you might have gone, oh, and I know how it's possible now during the course of this video. So I think you know, I called this a couple of slides back in which I will do part 2 of that, but I called it the God's Toolbox, and that should be little g O D S, and that should be in quotes, because I used to say to people about this technology, I guess since the beginning of 2017, that people probably through the entire history of humanity, when they've discovered little segments of what this technology can do, because it's really simple. It's really simple. Okay, they will have set themselves up as gods. They will, and greed, ego, and just straight tyranny. It's straight tyranny that's keeping people begging for scraps. Oh, we'll give you a little tax rebate. You know, your children will pay it back in 2 generations, but we'll give you a little bit tax rebate if you keep voting for us. If you keep voting for us. And we'll allow you to install wind turbines. And we'll allow you to install solar panels. We'll allow you to buy oil until you've got the other done. Okay? Bless. Bless. There must be a whole group of people that just laugh to themselves. They just must laugh to themselves. It's like, they fall for it every time. Like every cycle. Okay, I'm just going to see if you've got any questions through this. I'm sure you've just been chatting amongst yourselves, but... Asiandakun, you can start with business distill. Okay, so really I wanted to put this logic step together for you, Camillo, today, so that because I know you're going to start doing experiments in ultrasonics and you're specifically interested in Cardone work, and I wanted to just basically nail it. I have to say that I was happy with accepting Cardone's work, but when I saw, especially since Mercury was used by Shoulders and Tesla, but when John told me those, I mean, in those 2 sentences about talking about the molecular nature of Mercury, and but by the way, if you have a dimer of any atom, it's bosonic. It's a composite boson. It's a boson. It doesn't matter what isotope it is. Okay, it's always a boson, right? So that Hg 2 plus is a boson. Okay, it's absolutely perfect for making exotic vacuum objects. It's heavy, good to stabilize. Bucket loads of electrons. It's a metal. It's a metal at room temperature. I mean, you could literally, if you wanted to make an ancient technology for doing things that you could imagine ancient technology could do, you would use Mercury for very specific reasons. Okay? And then, yeah. I mean, those 2 sentences, there's literally a gold mine, a gold mine of information in those 2 sentences. And the fact that I you know, I'm sure someone out there, I didn't bother to do a Google search, which I could have done within 10 seconds, saying, you know, that Mercury effect radio frequency. Maybe someone else has thought about it. I'm sure they have. But the fact that it's not in Wikipedia and it's not mentioned by one of the leading authors in investigating this space, it just shocks me. And even if it is mentioned, it will never be mentioned alongside exotic vacuum objects and Ken Shoulders. And it should be. And that is what is transmuting the material in Cardone's work. And that is how we can use this technology to do something interesting for us. So the big problem in Fukushima is you can get rid of the other almost everything that comes out of a fission process that is a real problem are beta isotopes. and beta isotopes can be remediated with exotic vacuum object technology. The biggest problem is tritium, in terms of it's not necessarily the most radioactive, and it's definitely not the most long-lived. And you can do the excuse me. Dilution is the solution to pollution, which is the route they want to go down. But that does have consequences. It can't be quantified in the future, but it will have consequences. And the fact that we have a solution is one thing. But if you look at the reaction tables, I asked Alexander Parkhomov to add into the reaction tables tritium. So you can do reactions with tritium, and you will find that all the reactions, when you're using tritium instead of deuterium, it's more energetically favorable, which means it will proceed faster. So it is a wonderful, wonderful LENR fuel. It's such an amazing, valuable resource that they are going to throw into the ocean. It's just, you couldn't buy it if you wanted it, and they're going to throw it into the ocean, and it's a very valuable resource. Tritium will allow the production of other elements in a way that would be much harder, I believe. And you can see that by exploring the tables. Thank you for sharing the table, the directory with the Cardone papers, Camilla. Do you believe consciousness can produce EVOs? Yes, and I believe consciousness is in part driven by the stuff that goes into EVOs, and you can manipulate EVOs, and specifically you can manipulate EVOs that you generate yourself. They are tangled with your own consciousness, and I will talk about that in a whole other smorgasbord of presentations. It's part of O'Day. And there's several steps I need to go through to walk through the understanding. So yeah, I mean, there's all kinds of things that I thought people were absolutely bonkers about. I used to think that people went on about crystals, specifically quartz, and oh, it's got energy in it, blah 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 blah. And I used to think, oh, bless them. I had to eat humble pie. I really did. They're so right. They're so right. Okay, so you're going to start with potassium to calcium, yeah? So with these advanced physics concepts, are we moving closer towards a dystopian society like Blade Runner? Well, Blade Runner is dystopian in the 2000 whatever one it was, the last Blade Runner movie, right? It was dystopian. And guess what? It had solar panels and wind turbines everywhere. That's dystopian as far as I'm concerned. And that's what they're trying to force on everyone. Yes, we're going to Blade Runner if the money that is being extracted from many generations forward is going to be spent worldwide on absolute backward technology. Backward technology. No, the things that go into EVOs make a magnet, but a magnet is not really an EVO. An EVO is a coherent matter structure. Now there is coherence in the north and south of a magnet, but not to the effect that you can do what you can do with these. I mean, you're talking about an extremely large amount of matter. So when you're looking at what I'm showing you, when I'm let me show this. Okay, so when I'm showing you this here, they've got a large number of whatever it is cesium ions in this coherent structure. Okay, somewhere in the center of this structure, I believe there will be a void, and that will be where the real action is occurring. That has happened here a long time before we saw this, and as it grew, it ate more and more of the material in this sphere, so what probably is on the boundary layer of this sphere is incredibly dense, and the magnetic field here is highly localized, because it's kind of, anyway. The point being is that this has some magnetic properties, but it's very much not like a normal magnet. The Geller-bent spoon, are you referring to the one that Dr. George Eagley had? Dr. George Eagley told me that he was with Uri Geller at one point, and he bent a spoon or a fork. I think it was a fork. And it was on the table, and he took it just because he did, and it continued to bend for a long period after he took it. And so I would imagine that the bend has these crystal grain effects going on that you would see in Takaaki Matsumoto's work, something like that, and in the work of John Hutchison. What sort of work would be worth doing with the synchrotron, James? Well, you can go and look at the work of Bogdanovich published in 2019, May, I think it was, and he showed that he could create the birdie-shaped quanta of strange radiation using synchrotron radiation going into conversion targets, producing gamma rays, and then the gamma rays going across the poles of a magnet. And he would create the two types. An EVO is not unlike an asymmetrical capacitor with a gyroscopic motion surrounding it. Would that be a correct assumption? Well, it's the best description. I have a video on YouTube called "Hacking the Neutrino Universe," and I think basically that does it. Really, it talks about the Boyd-Bushman pseudo-monopole magnet or directional magnetic beam, and that's essentially what you're seeing in these structures. And well, when I say magnetic, it's directional magnetic, but it's also gravitic directional as well. Sooner or later, you're going to work out how easy it is to do propulsion. Let's call it that. Ken Childers used to say, don't give me anti-gravity, I prefer propulsion, and that's because it can do that. Anyway, we're going to get to that. What would be easy to do, and in your opinion demonstrate results that support your theory's knowledge in synchrotron? Or same answer. I mean, I have a use for a beamline, but I've already identified the supply, and that's when I run the stuff in the supernova reactor. I just want to look at the 12, 13, 14 carbon ratio and see if the reactor has created sufficient EVOs to take my charcoal, which is a couple of years old from Germany, and make it into 50, 60, 70,000 years old, and then it's 100% proof. I proposed this a long time ago, but I'm now willing to use the reactor, and I have the last part of my shielding, so I think I'm going to go ahead with that, and then that'll 100% prove that within a few minutes you can make something appear as if it's 50, 100,000 years old, and the only way that could happen is if the 14 carbon made beta decay to 14 nitrogen. So that's that test. The test that I hypothesized with the thallium 205 moving beta, forced beta decay, it's perfectly natural till the end of the universe, as long as you don't remove all the electrons. Now, exotic vacuum objects remove all the electrons, and so it will decay, and I believe that's what happened in GS 5.2 when there was what looked like an exploding EVO, because we had our power monitor go down, which is typical for an EMP, and we had this spike with no characteristic X-rays all the way up into the gamma. And the only way that can be possible, in my view, is it didn't go through any metals, but it was actually inside the thallium-doped sodium iodide scintillator crystal when it EMP'd. And so all of these fast beta particles came out, and the EVO itself split up, the macro ball lightning, and it went in there, and it caused transmutation of the thallium. And so that detector is actually with someone at the moment, and they believe they have invented a technology to determine the difference between in mass, or be able to detect the thallium 205 and the lead 205. And if that's true, that will prove from a different angle, because if there's lead 205 in there, it's not natural, and it has something like a 10 million year half-life. So that will be 100% verifiable proof every day of the week that something went into that crystal and produced something that shouldn't be in that crystal in so on. So at the moment there's two tracks to proving that side of things, and one is well underway and one's nearly underway. But in terms of a synchrotron, you could investigate, because the synchrotron will create these birdie shapes, but the birdie shapes are that, whilst they are able to kill you because they carry ions with them, and they can eject them at energies which are fast enough to cause red blood cells to die and white blood cells to have DNA damage. So you don't want to be around it when you're doing that. The energies they're not able to be clustered easily in a way that is able to do what John Hutchison is doing, really. Dear Don, I have reviewed the videos you sent me. I like the early one where the two filaments join together, and I will try and find a way to fit that in the next week, I think, after I've done the part 2 of Something Electric. And I also like the with the nanocarbon at the bottom, but anyway, I like the thing moving around there, so there's something to think about there. So thank you for that very much. Would there be a way to apply this on a Vasimir rocket engine? Don't know. Gardy, don't know. I'd have to know what that was first. WP for truth. In building a reactor, what material would I use to contain the tritium while transmuting that would not break down? Not quite sure what you're asking, but if you're using LENR, it won't tend to produce beta radioactive isotopes. It shouldn't do. In fact, the energy equation doesn't permit it to. it's a non-permitted reaction. Now, having said that, you could have you could push it too far, like Leclerc did, or like Spherical, and you go beyond bismuth and you produce radioactive isotopes that then split, and then you get beta isotopes out of that. But if you're working down at the bottom end of the periodic table, or you have heavy elements with a lot of light elements, like, you know, you've got potassium and you've got lead or mercury or bismuth, it tends to average into the middle, and it's only when you push it up, and it's a statistical thing. You know, if you can arrange your nucleons in a packing density easily with a quick win to get it into a much smaller box, you will. But if you're pushed up against it, and this is the case of if you make very, very energetic exotic vacuum objects, you will create what Sviatomenko did, 455 AMU nucleons, like that are heavier than anything in our near universe. You don't want to do that. This is something that you have to use with respect, and you don't push it too hard. Oh, and you could also convert things into like light and electrons, and you don't want to do that either. Or neutrinos. As I've said in this paper, you can convert matter into... You get a unification of the forces. Solin observed this. I think we've observed that in a number of different experiments. And this can convert it into like protomatter or prima materia, and that can become photons, that can become electrons, that can become neutrinos, and so some of these things can be completely lost. How do you use the beamer? It's this. This is the beamer. This is the beamer. It's in the zone between it, but you're never going to be able to get a strong enough magnet to do this. But nature makes this itself. It's self-organizing this structure. Yeah? It's self-organizing this structure, which does this crazy stuff. Oh, Gardy Pierre, the Vasimir is a rocket engine. You won't need to eject material when you use this technology, and I will explain that long after I've done the second part of something electric. Why did Boyd design it? Well, you can use it. You could use it, for instance, to direct EVOs, maybe. Contain EVOs. You know, there are things you can use these things. He made a patent because he observed when you put two magnets back to back and you drop it from a tall building, it doesn't obey, you know, the normal laws of gravity. Man-made laws. And so he thought about that, and he came up with that structure, and that structure is quite important. And if you want to see what it can do, then go and have a look at the primer fields. But the primer fields bowls are essentially the pattern, the Lockheed Martin pattern, and all the guy from primer fields has done is removed the bottom magnet. It's the same thing. So you can do all kinds of things with that. You can control plasma, and plasma leads to self-organization. Even the best tokamak in the world is always struggles with Darkatron stabilities and Poincare problems and all these things that lead to exotic vacuum objects being made. I think Okay, good. And I'm about to go as well because it's nearly one in the morning here, so I need to go. So I think join the technicians. Go and look at the primer fields guy and what he's managed to achieve with effectively a version of the patent. So W for truth are those gold formulas on your site. If you go to my Steemit blog, which is Steemit, well, it's the MFMP's one, at MFMP, and it's an article I wrote 3 years ago, and I walk through the whole process, the fact that strange radiation is causing it, strange radiation is EVOs, and so on, and the reactions for the various alchemical metals, and that I recommend bismuth. That was over 3 years ago, but I believe probably that I'm pretty sure that cavitation is the better way to go, and in the case of bismuth, if you wanted to do metal-metal interactions, you would have to heat it up, and then you would have to be in a safe environment if you're putting an alkaline metal in there. But yeah, fun and games, really. It's all there, really, and then you can go and do your own reactions on nanosoft.co.nz. Here, the MFMP's reaction calculator, and so forth. And you can watch this video with how I'm doing it here, but Philip's got some notes and you know how you enter things, but it's clearly described here. Once you get the hang of it, for doing the basic stuff like this, it's pretty easy. What's funny about this reaction calculator is, like, you can just go to any of the Lena literature, and what they observe is what this calculator calculates. So, you know, that gives you a lot of confidence that it's going to do that. But like I say, you're having to go all the way down to here. You know, there's a lot of other reactions that occur before, and they're like 4 times more favorable. But like I say, it's statistics. Given your environment and some parameter spaces, and you know, I've given this to everyone because it's not mine to keep. This is a human and our species' right to know this technology. But if you find a parameter, you know, I would hope you would give back to the broader community, because we should be living in a world of plenty. That being said, if you have got lots of active EVOs, then you need to be playing safe with this. So, you know, you need to think about that and look at the work that we've done with looking at shielding and so forth. But I think metals that have a low level of exotic vacuum objects bound into them, you know, they're probably quite special. That's why I chose a single nugget. I chose a single nugget of gold from Alaska. The reason I chose for our Reading rings is because it was shown by the French and Reitskev. They went up to the tundra and they recorded strange radiation tracks naturally coming in from the cosmos or being emitted from the Earth or whatever. So the point being is metals will hold on to these quanta of EVOs for a very long time. And so my view was, if I took one nugget, there will be quantum entangled material in there, and when I split it, both of our rings will have exactly the same quantum entangled material in there. And so that's why I chose that. So you know, these things are not done for no reason. In my case, anyway. No, I think consciousness is able to interact through the same medium that is able to coalesce into evos, and life forms can interact with this material as well. And I think the Russians would call it microleptons. And there has to be a medium that's available everywhere for consciousness to work. And you know, for you to be able to attach to the Akashic record and those kind of things, you know. I always remember my friend, she had a brain tumor the size of a fist, and they said she wouldn't walk, she wouldn't speak, blah, blah, blah. But I ended up acting on the stage with her for 9 years, and she got her memories back. And so somehow they're like fractally encoded in the brain, or that you have a key to the Akashic record and you have your own personal cloud, as it were. Something's going on there, and you have your own frequency as a sentient organism, and when you create exotic vacuum objects, they are linked to you. But like I say, I'll go into there's a whole other area of this that needs a lot of work to get it across. What did I miss? Going to repeat all that? You're so funny. You start at the beginning, word to the end. Okay, so I'll just run through and then I'll call it a night. So a quick summary. Let's put it that way. So we started off saying this was no coincidence, and it's no coincidence. The one on the left is from 1986, and it's on the Bullburn sample, and we showed it over here on the Bullburn sample under the Dynalite. And on the right, it's from 1988 as far as we know, and that is very much larger. This is 400 microns across, and this is very, 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 very big. It's like you can hold this sample in your hand and it fills up most of your hand. And then I showed that these things, they're exactly the same shape. They're slightly distorted hexagons, and then it has the round bit in the center with vortical structures and so forth. And then this is the inside of it, and we talked about that. And then this is the close-up of the structure over here on the scanning electron microscope, and you can see that it is a torus with this tail, and it has a D4D structure, and so does the well, this is a torus with the tail on the light luminous toroidal object that was found 2 days after a plasma flow discharge at the Moscow Nuclear Physics Laboratory. And then we saw this with a little bit more detail. No, if I go back. Here, a little bit more detail, so we can see the scallops on our yin-yang, which is 2 hexagon structures with a tail pushed over here. And then there's our trefoil there, and then here is the structure that I wanted to focus on again today. And the first time I took a picture of that, it had a reflection here on the outside and an internal reflection from a much harder studio light than this, and I used a 7D and this 35mm macro lens. So I wanted to see closer into this to see this really, if this really was a sphere, and I used this Narugo $70 microscope on a Samsung S7, and I found all kinds of different structures. So this is a Paisley type structure going into the point. This is this is a 1 point, and this is 2 things in here. So you've got a structure over here and then another one over here, and so we see these in lion and things. So it gave me this look, which does show refraction going on, but I couldn't look into the hole, so I needed to use a different technology. Now, under the SEM, what I did notice was, under the SEM, I did notice that you could see the sphere underneath. So clearly there is a sphere underneath. So I managed to get my macro lens to give me enough of an image with a sharp highlight. So this is again from the studio light, but it produced a square reflection that's and the angle from there points to the fact that this really is a spherical object that's depressed and 50% in and 50% out of this structure. And also to note was that in this thing you have these scallop sections taken out which run all the way into the spherical structure underneath. Now, this double reflection in here made me think that this was maybe a skin, and could this be the coherent matter layer and it's left, and what is it made from? But is it a thin layer? Because there's evidence in the record of that being possible. And then so I looked at the work of Bitchkoff, who has this image of ball lightning. And the ball lightning has cut a section out of this, and it has a north pole and a south pole, a north pole and a south pole, and you've got the material sort of coming in and affecting the glass. And I explained that as this goes through glass, it's probably getting to a 50% area through this, and it starts to the poles start to interact with the actual glass impedance difference between one side and the other, and it gets trapped there. It excites the coherent matter layer boundary, and that eats a piece of glass, and then it's able to go on its way. And so I believe that this will be slightly smaller. I said I wanted to see the boundary here because I thought it would be exactly the same as we've seen on the Lion. And this is when I then got the Dynalite Edge, and I looked at this again. Again, you can see that this is this funny kind of like not question mark, but quote mark shape in this glassy area here. And I used depth of field, and I can actually show that the bottom, if I focus into the bottom, it's in focus at the bottom, but as it comes up here, it goes out of focus, and then it's got this hard edge. So this means you've got a tangent at this point, and that this is in focus here, and as it comes up, this means this is confirmed to be a hemisphere under here, and that means that we have with this refraction going on, and this hard line around here, this absolutely is some clear, extremely hard, solid stuff in here. And so when I analysed it under the SEM, I found out that this was basically carbon, and therefore this is likely to be diamond. And with what we know now from Matsumoto and from our own work and from the work of Yul Brown, this technology will produce carbon predominantly. This could be a carbon sphere, a diamond, a pure diamond sphere, which would be essentially the same as the shapes that I was showing under the Fu Dogs in the Forbidden Palace in Beijing. And then I talked about this paper, which is a fairly recent paper. It's published. They published several things in Nature, but they managed to create this extremely small cesium-133 coherent matter structure, which forms into these structures. And I'm saying that this is a very much larger version of this. They think they've discovered something new. They haven't. John Hutchison was doing this many decades ago. And in the center of here, I believe that there would be, it's not a singularity, it's a point of the unification of the forces, and basically it grows. And so if this wasn't so incredibly small, you could end up with a big one that looked like this, and it would basically transmute the matter in the point here. And then I went on to talk about Mercury, and how John Hutchison had given a throwaway comment here about Mercury producing static and causing discharges and radio frequency. And then I talked about how exotic vacuum objects, I talked about this, blah, blah, blah. You can go back and see that. And then I talked about the structure that I deduced from the physical evidence of John Hutchison, and these areas that are eaten out and not eaten out, eaten out and not eaten out, and eaten out. And so there had to be something that is static in place, and static in place at the lower quanta here as well, because it leaves lines on here and so on, but different. That it needs to be static. And so I'm saying that this is static structure, but it's able to shift material around it, and it has a both a magnetic and I believe a gravitic structure. And then we come to this, which was shared with me yesterday, and I saw this for the first time yesterday, and it was written in 1954 by one John Archibald Wheeler. And he's just reviewed this. It says, regions of strong electric field strength in a simple toroidal geon of zero angular momentum. So it's not spinning round, which is exactly what I'm saying this is not doing. And this is derived from John Hutchison's sample as a physical evidence witness. And in this case, it's not spinning round, but these areas are high electric field strength,
Two waves of equal strength run around in torus in opposite directions to produce a standing wave. So I've been talking a lot about standing waves and the importance of standing waves. You've got one coming around this way and one coming around this way. So they're the two standing waves, with electric fields strong in the regions indicated, these areas, and magnetic fields strong in the regions in between. So these gaps in between are strong magnetic fields. Okay, and so this would basically exactly follow what the evidence that you're seeing here. So the electric fields would interact with the aluminium, and the magnetic fields wouldn't so much. So you end up with this these features on here. The gravitational field created by this disturbance and required to hold the disturbance together. So there's a gravitational thing that is able to hold this structure together. Is represented by a good approximation as a static and independent azimuth. So here we go, and I believe that this is the gravitational thing that's going off. And I talked about why in the Lion reactor we had things that were gravitationally aligned, and this was also mentioned in the work in 1957 by Winston Bostick, that there's some interaction with gravity going on. So it is actually Bostick's work and some other work around that time that led me in 2017 to believe that most of the key parts of this technology were worked out in between the mid 1950s and early 1960s. And then this was published yesterday, and they think they've done something new and interesting, but it's not. Sorry, they think they've done. They've got this nice hexagon shape here with the little balls in between, which we've seen in the structures I showed you earlier, and it's a D4D structure, and this is a super cooled molecules in a coherent state, and that's what John Hutchison's doing all the time. So that it looked interesting. It's in Nature or whatever. This is in Physical Review. This is not published anywhere but YouTube, and so on. And John has never been in a scientific paper, thankfully. Otherwise, I probably wouldn't have such wonderful golden opportunities to decode what I'm seeing. And then so I talked about with the Mercury and the fact that exotic vacuum objects can do all this. The fact that this guy Cardone and his colleagues are observing transmutation in Mercury. Mercury, this is a cavitator using ultrasonics into Mercury. And I'm saying there was a thing that John pointed out, that Mercury can produce flashes and radio flashes, that therefore it's making EVOs. So EVOs will be the thing that's doing the transmutation. And then I talked about how to make gold, because there's several people that have asked that question. So this is a more specific method than the actual elements that I recommended more than 3 years ago in my Making Gold presentation. And so I gave direction for making gold, and I said that you could start with water and stuff, but water will need to progress through all the other elements in the periodic table, and you'll be shaking it for an extremely long time. You might make a very little bit of gold, but it's going to take a long time, so you'd be better off starting with things that are closer to it, and playing the odds on the statistics. And then I walked through the likelihood, which is slim. And I think you can see here that we can see gold if we're starting with calcium and bismuth, and we've got these in some sort of mixture, and we're ultrasonically exciting these things. Depending on the other parameters, which are all obvious and they can't be patented, they're basically all obvious what you could change. It looks like it's the most likely, but you could end up with a whole load of other valuable elements in the process. There we go. So that was basically it, really. It was kind of like basics of electro-gravitics. The fact that John Hutchison absolutely 100% has been able to replicate, and that he could not have faked this. This is not a faked shape, because this is just 400 microns over on this microscope over here. It's 400 microns across. And by the way, that 400 microns across the diameter there is exactly the same scale as the quanta of this. So this is 200 radius, that's a 400 micron radius across there. This is exactly the same quanta of exotic vacuum object as you are seeing in the title slide. And so there we go. This was no coincidence. And it is no coincidence. The fact that this is micron style, and the fact that it's exactly the same shape as the Bogdanovich work, it's absolutely impossible that this is faked in any way. John Hutchison's technology is real. It is transmuting matter. It is coherent matter waves. It's nothing. All of these papers that are claiming all kinds of nonsense first. John did it first. John Hutchison did it first. Maybe Tesla was able to transmute matter. I don't know. It's, as far as I'm aware, it's not specifically noted anywhere. But John used all kinds of things that weren't available to Tesla. So I think John Hutchison is the main man, really. Hey, Field Interference, great to see you on the channel. And thank you for your kind words. John Archibald Wheeler is someone whose AS researches. I don't know. Infidel Apostate says, once someone feeds the AI digital LSD. I said when in, I think probably 2017, I said this will be the last great technology to be invented by man, but I then coveted and said that it's not an invention, it's just a realization, because it's already been used by our species, probably in multiple cycles. But we need to not to abuse it, because you can strip the planet. I said everything else would be invented by AI after this. But the great thing is that this is all there is, actually. And the other brilliant thing is, it completely stops semiconductors from working. By the way, if you get a big one of these, you'll have weird effects on your consciousness, and you may lose time, or even your time will stop. And we'll talk about time travel. It's relatively easy to understand how you can effectively go forward in time with this technology, but I can't work out how to go backwards in time. Just can't work out how to go backwards in time. Yeah. WP for truth. Do plants contain EVAs? I believe they do, and I believe they don't if you put them in a microwave. I mean, not entirely, but I think food that's been in the microwave this is a whole other topic. It is actually a slide or two of O'Day's anyway, or one or half, maybe one bullet point, but anyway. You will disrupt them, and for the same reason that anti-gravity craft fell out of the sky when they started using radar. Which was based on micros. We know from the Perovskikov work that water can collect quanta of this radiation from the environment, and therefore water-bearing plants will collect quanta of this radiation from the environment. And I believe that cells in plants use it for transmutation, and therefore it will be in there. Small doses of this, like for instance the Germans have done work with the Russians where they take corona discharge into water that's then given to seeds, or Shishkin uses cavitated water and puts it in seeds and gets better and faster germination. So life likes to have a certain quanta of this in water, and that was my Elixir Vitae presentation. I talked about that. So if you remove this energy form and this ability to rebuild yourself, the subtleness of it, and you remove that from food by either irradiating it using gamma rays, like you do when you irradiate fruit so it lives on the shelf for a long time, or you put it in the microwave. These two things will remove the gently gathered, extremely good exotic vacuum objects. Contrary to that, boiling food will not damage them. Boiling food or slow cooking, but specifically microwaves and actually coherent radiation. If you, it would be a lot slower. But if you got a laser and put it all over your food, it would do the same thing, just like it does in the perovskite work. So yeah, you know, I keep saying by the time I'm finished, everyone's going to hate me. Everyone's going to hate me. Everyone. It completely. It just changes everything. So like. You don't want, and I can do it for you now. I mean, I if I got my, I'll do it in another thing. But if you get a phone, and you put it near my microwave detector, it's off the scale. It's so far out of the legal limit for 1 meter away from your domestic microwave. And it's basically, it's not surprising that people have, like, there's an Australian woman, she shows that a woman who kept her phone in her suit all the time, and it, like here, actually had a cancer on her breast that was the shape of the antenna of the of the phone. It's not, I shouldn't laugh, but it's like at what point do people start accepting it? So I basically turn my phone off and the Wi-Fi off at every single opportunity, and it annoys my family a great deal. And I only microwave a few things. Other than that, I slow cook. And I don't like to buy fruit. I like to harvest fruit or grow my own vegetables because I don't want irradiated fruit. If a bug doesn't want to eat my fruit, I shouldn't want to eat it too. That's as far as I go. The moon is extremely important in this context. Go and have a look at, if gravity does this, what is gravity? Go and those were my early kind of like, it's been such a long journey to get to these presentations I'm giving you now, really. How much planning this has taken. So much planning. Because I would speak to people, and it's like I would get like 10 minutes or 20 minutes into the conversation, I realised they've already had enough. So I realised this is going to literally take years. It's going to take years to go through. And the other advantage of going through years is that you don't have to rely on the evidence that was enough for you. You can picture, you can do experiments, you can visit experimentalists, and you already know if it is this technology, it will exhibit X, Y, and Z, and so you don't go blind, and then you know kind of what you want to take, and then you can look at it, and so that's how you build the evidence up. So So the seed experiment, some people fail with the seed. Oh, the seed with the magnet. Yeah, the magnet will do that. Why does the magnet do it? It's just, it's putting coherent exotic vacuum objects subquanta in. Like if you put the South Pole, it's pushing the stuff in. It's trivial, but it's basically derived off the Perovskite work. You only need to look at the Perovskite work, and you'll you know. My presentation on Elixir Vitae was kind of like, well, there you go, that's that. This is the God's toolbox. I mean, it's just a beautiful thing, and there is really nothing after this. But as I said to them in Aarhus University, there will be whole universities that are dedicated to studying this. Otherwise, we've just gone wrong as humanity. We've just completely gone wrong, because we are. What I will show you on Sunday, assuming I've got the energy to do it now, what I will show you on Sunday, it just makes ITER look a joke, just a joke. It's just a joke, just a complete joke. It's just a joke. What upsets me is I really care if people are wasting their lives. There are all kinds of people inventing useless things. They're useless, but they don't know they're useless yet. But if this technology had not been stifled, and the right minds had looked at it sooner, if John Hutchison had been taken seriously more than he was by one of the most intelligent inventors ever, Ken Shoulders, if he'd been taken more seriously, then we could be so far ahead. There is this problem that it doesn't play well with semiconductors. I mean, you can deal with it, but because semiconductors or silicon chips, they are a quantum effect in many ways. That these things, you can have a super civilization that uses exotic vacuum objects, and you can have a think they're super civilization that are stuck in front of screens being told what to think. Oh dear. Okay, I'm going to call it a night, guys. So thank you. It's been a pleasure. Thank you for your time. And I'll say arrivederci, dobro noc, buenas noches, buonasera, bonne nuit, good night. And hopefully I'll see you on Sunday in Something Electric Part 2. See ya.